Hi everyone, welcome to goclasses. In this lecture, we will study semantic analysis. Also, we will see the introduction to SDD, syntax directed definition, and also syntax directed translation. In this lecture, in detail, we will study syntax directed translation, also syntax directed translation schemes. All these concepts will become very clear by the end of this lecture. So let's start. First, we will study semantic analysis. So in the compilation, where are we? So far we have seen lexical analysis, syntax analysis. Now we will study semantic analysis. You can see the lexical analyzer, what it will do? It will read the source text. The source text, the source program, it will be read by the lexical analyzer. And this lexical analyzer will convert our stream of characters, or I can say this lexical analyzer will convert our source text into a sequence of tokens. So basically the lexical analyzer will perform the lexical analysis. Then syntax analyzer, or I can say parser, will perform the syntax analysis, or I can say parsing. Now the output of parser, that is a parse tree or abstract syntax tree. So the output of syntax analyzer, that is a syntax tree or abstract syntax tree, that is the input to the semantic analyzer. The semantic analyzer will perform semantic analysis. Semantic, this word, what this word means? This word means the analysis of the meaning. Okay, remember syntax means the structure of the program, and semantic means the meaning of the program. So in the syntax analysis, we we do the analysis of the structure of the program, and in the semantic analysis, we do the analysis of the meaning of the program. Meaning of the program means what the program does. When the program will execute, what the program will do. So that is what we mean. That is what we mean by semantic analysis. Okay. So you can see here in the compiler overview, you can see that for the semantic analyzer, the input is syntax tree. The output of the syntax analyzer, that is syntax tree or abstract syntax tree. So that is the input to the semantic analyzer. And the output of the semantic analyzer, that is annotated syntax tree. Okay. Now let's start. So here you can see where are we in the compilation process. So far we have seen the lexical analysis, means so far we have verified that our program, our source program is lexically well formed. Lexically well formed, what it means? It means that the identifiers have valid names, the strings are properly terminated, there are no stray characters, basically there are no invalid characters. Okay, so this is what we check in the lexical analysis phase. Now also we have done the syntax analysis, means we have already verified that our program is syntactically well formed, means the structure of the program, the syntax of the program is correct. The structure of the program or the syntax of the program is according to the grammar of the programming language. Okay, very simple. So you can see the program is syntactically well formed, means the expressions are syntactically valid. Okay, if you have C++ language, then class declarations have the correct structure. So basically in this syntax analysis phase, we do the analysis of the syntax or the structure of the program. Okay, now if our program is lexically valid, if our program is syntactically well formed, then can we say that our program is legal? The answer is no, because we also have to do semantic analysis. Along with lexical analysis and syntax analysis, we also have to perform semantic analysis. In the semantic analysis, we ensure that the program has well defined meaning. Okay, I told you that semantic, what this means? This means the verification of the meaning. Okay, so in the semantic analysis, we ensure that our program has well defined meaning. Okay, so basically we verify some properties that we could not verify in the earlier phases. In the syntax analysis phase, in the lexical analysis phase, in those phases we could not verify some properties. So those properties we will verify in this semantic analysis phase. Okay, you can see in the lexical analysis phase, we use regular expressions, In the syntax analysis phase, we use context-free grammars. And you can see context-free grammars and regular expressions, they cannot handle the context-sensitive information. There are, in the programming languages, there are some constructs which are context-sensitive. So those context-sensitive constructs, those cannot be handled by lexical analyzer, also syntax analyzer. So those we can handle in the semantic analysis phase. Okay, so you can see here that in this semantic analysis phase, we ensure that the program has well-defined meaning, and we verify the properties. We verify the following properties. There are some more, of course. Okay, so you can see that we verify the properties of the program that we could not verify in the earlier phases. For example, in this semantic analysis phase, what are the important things that we do? You can see we verify that the variables are declared before they are used. In the C language also, you can see the variable in the C language, the variables must be declared before we use them. The expressions must have the right types, means the type checking we have to do. Okay, for example, you cannot add integer to a string and an integer, you cannot do the summation. Okay, so you can see that the expression have the right types. Okay, so basically type checking, that is an important task of semantic analysis phase. Also, you can see some other properties also we verify. I will also tell you some more important properties that we verify in the semantic analysis phase. I will tell you as we go on. Okay, now you can see once we finish semantic analysis, now we know that user's input program is legal. Okay, you can see lexical analysis, syntax analysis, semantic analysis. Once we perform these three analysis on the source program, then we can say that the user's input program is legal. Okay, very simple. I hope you understood. Now let's study syntax versus semantics. This actually we have already seen when we were discussing syntax analyzer in the previous lectures, where we were discussing the syntax analyzer. This difference of syntax versus semantics actually we have already seen, but let's revisit again. Let's revise this again. So you can see, first let's see a simple analogy to understand syntax versus semantics. Remember syntax, you can see syntax is like the correct English grammar. For example, he go to school. Now this is wrong English grammar, so we can say syntax is wrong. You can see he goes to school. Here the grammar, English grammar is correct, so I can say syntax is correct. So you can see that syntax is basically like the correct English grammar. Now you can see semantics. Semantics is the meaning, means the meaning should be correct. Okay, in the semantic analysis, we ensure that the meaning is well formed. In the syntax analysis, we verify that the structure is well formed, or I can say that the structure is according to the grammar of the source programming language. Okay, very simple. So you can see semantics analysis. In the semantics analysis, we do the analysis of the meaning. For example, the cat drove the car. Now the grammar is correct here. You can see the cat drove the car. Here the grammar is correct, but the meaning is wrong. So here the syntax is correct, but the semantics is wrong. I hope you understood this analogy. Okay, now let's see here syntax versus semantic. Remember, in any programming language, for a program, we need to do syntax analysis as well as semantic analysis. In the syntax analysis, we do the analysis of the structure, or I can say we do the analysis of the grammar or the analysis of the form. Basically, in this syntax analysis, we verify that our program, our source program, is according to the rules of the grammar of the source programming language. Very simple. Okay, so you can see in the semantic analysis, we do the analysis of the meaning. We ensure that our program has well defined meaning. Very simple. Now you can see this, you can read this. The syntax of a programming language describes the proper form of its programs, while the semantics of the language, it defines what the program means, what the program does when it executes. Okay, very simple. So syntax of a programming language, it is basically related to the proper form, proper structure, proper statements according to the grammar of the programming language. While the semantics, this is related to the meaning of the program, means what the program does when it executes. Very simple. Okay. Now let's see some examples of syntax rules. Then we will see some examples of semantic rules. So here we have some examples of syntax rules, means these things we will catch or these things we will verify in the syntax analysis phase. Okay, so you can see some examples of syntax rules. For example, parenthesis must be balanced. You can see if you have open parenthesis, then there must be a corresponding close parenthesis. Similarly, if you have open left brace, then there should be a corresponding right brace. Okay, very simple. So you can see, for example, this should not happen. Here you can see we have left parenthesis, there is corresponding right parenthesis, but for this right parenthesis there is no corresponding left parenthesis. So you can see that parenthesis must be balanced, and this we can check in the syntax analysis phase. Basically, with help of context free grammar, with help of CFG, we can verify, we can check that parenthesis must be balanced, or I can say the braces must be balanced, or the brackets must be balanced. Okay, next you can see keywords. Keywords must appear in the correct order. For example, if, then else. Okay, it should not happen that then is coming, then if is coming, then else is coming. It should not happen. So you can see keywords must appear in the correct order. This also we can verify. This also we can describe using context free grammar. Okay, so in the syntax analysis phase, this also we can verify. Now let's see some syntax errors. So syntax errors will occur when the source program doesn't follow the grammar. Let's see some examples. For example, missing semicolon in the C language. In the C language, every statement must end with semicolon. So if there is a missing semicolon in the C language, then you can see this is a syntax error. Next you can see unmatched right brace. So basically this has to do with that braces must be balanced. So you can see if you have unmatched right brace, then definitely this is a syntax error. Next you can see if you are writing like this, if x greater than 0, instead of writing like this, if then parenthesis x greater than 0. So you can see this is in the C language. If I talk from the C language point of view, you can see this is actually correct syntax. But if you write like this without using these parentheses, then this is a wrong syntax. So you can see if you are writing like this instead of this, then this is also a syntax error. Very simple. Next you can see operators must appear between operands. For example, it should not happen. You can see AB plus C like that. It should not happen. Okay, you can see A, B, so there should be multiplication or there should be addition. Basically, operator must appear between operands. Okay, so you can see these are some syntax errors and these are some syntax related rules. So these syntax related rules, these can be described using context free grammar, and these we can verify in the syntax analysis phase, and these syntax errors we can catch in the syntax analysis phase. Okay, very simple. So let me tell you in detail actually all these syntax rules that we have seen. I told you that these syntax rules we can describe using context free grammar, and the syntax analyzer, it uses context free grammar. So the syntax analyzer can catch the syntax error related to these rules. If these rules are not followed, then there will be syntax error, and this syntax error will be given to the user. Okay, very simple. So let's see here. You can see, for example, you can see all the syntax rules can be described using context free grammar. For example, parenthesis must be balanced. For balanced parenthesis, actually we have context free grammar. If you remember in the theory of computation subject, in the automata theory subject, for the balanced parenthesis, there is a language balanced parenthesis. For that language, we can write a context free grammar. For example, S can go to, if there is a left parenthesis, then there should be a corresponding right parenthesis. Okay, yes or no? And in between, again, you can have balanced parenthesis. Okay, so you can see left parenthesis, then there is corresponding right parenthesis, and in between, you can have Again, you can have balanced parenthesis. Okay, then SS. So if you remember this type of language, this balanced parenthesis language we have seen, and the grammar, the context-free grammar for that balanced parenthesis language also we have seen in the theory of computation automata theory subject. Okay, so you can see epsilon. So you can see this is the context-free grammar for balanced parenthesis language. Okay, so I hope you understood. So you can see that parenthesis must be balanced. This is a syntax rule, and we can describe this using context-free grammar. Very simple. Now let's see this. Keywords must appear in the correct order. So for example, you can see that expression can go to if, then expression, then expression, else expression. Okay, so like that. I hope you are getting the idea. So you can see that using context-free grammar, we can make sure that the keywords appear in the correct order. Okay, so you can see this is also a syntax rule, and we can describe this using context-free grammar. Because we can describe this using context-free grammar, so in the syntax analysis phase, we can verify this property. Very simple. Let's see the next. Statements must end with semicolon in the C language. This is also very easy to describe using context-free grammar. You can say, for example, if S is a statement, then I can say that S will determine, okay, something, and you can end with semicolon. Okay, so like that. I hope you are getting the point. So you can see whatever S will derive, basically the statement must end with semicolon. Okay. Next, you can see operators must appear between operands. Again, this is something that we can describe using context-free grammar. For example, you can see expression going to expression plus expression, or expression multiplied by expression. Okay, like that. Okay, you are getting the idea. So you can see that we can make sure that operators must appear between operands. Here you can see operators, they are appearing between operands. So you can see that this property, this rule, we can describe using context-free grammar. So this is also syntax rule, and we can catch if there is any error related to this rule. If this type of situation is there, then there will be syntax error. I hope you understood. Okay, very simple. Now let's see some examples of semantic rules. Some examples of semantic rules. You can see you cannot divide by 0. This is a semantic rule. I will tell you why. Okay, that we will actually discuss this. So you can see you cannot divide by 0. Basically, we cannot divide by 0. That is a semantic rule. Also, type matching, type mismatching, these are also semantic rules. Basically, the type must match. You can see variables must be declared before use. This is also a semantic rule. So remember, all these properties we need to verify in the semantic analysis phase. Okay, so you can see these properties we cannot verify in the syntax analysis phase or lexical analysis phase. So these properties we should verify in the semantic analysis phase, and these are the properties. You can see, for example, type matching, divide by 0 means you cannot divide by 0. Variables must be declared before use. Function call must match the function declaration. Okay, means when you are calling a function, then let's assume when you declare the function, let's assume there are 2 parameters, and if you are calling the same function, then let's assume you are providing 1 parameter or 3 parameter, then definitely function call is not matching the function declaration. So that is a semantic error. Okay, so you can see these are the semantic rules, that function call must match the function declaration, variable must be declared before we use it, type must match, you cannot divide by 0, like that. Now what are the semantic errors? So you can see if you divide by 0, that is a semantic error. Okay, also type mismatch, that is a semantic error. For example, if you do the addition of integer and string, then there is a type mismatch. Okay, so this is also semantic error. Next, you can see function call that has wrong number of parameters for the declared function. Let's assume foo is a function, FOO. Let's assume foo is a function that is expecting 3 arguments, but you are providing only 2 arguments. When you are calling this function foo, you are providing 2 arguments, but the foo function declaration has 3 arguments, means foo function is expecting 3 arguments. So you can see this is a semantic error. I hope you understood. Okay, very simple. Let's read this. You can see semantic analysis. The semantic analyzer, it will use the syntax tree and information from the symbol table. You already know that for the semantic analyzer, the input is syntax tree. So remember the semantic analyzer. This semantic analyzer, it will use the syntax tree. Also, it will use the information stored in the symbol table to perform the semantic analysis. Okay, so you can read this, that the semantic analyzer uses the syntax tree because the input of semantic analyzer, that is syntax tree. So the semantic analyzer will use the syntax tree and the information in the symbol table to check that the source program, basically to check the source program for semantic consistency with the language definition. Okay, means the source program has well defined meaning according to the source programming language. Okay, so you can see that the semantic analyzer, it will basically check the source program. It will check the source program for semantic consistency with the language definition. Also, what it does, the semantic analyzer will also do some extra things. Let me tell you. For example, it will gather the type information and it will save this information in the symbol table or in the syntax tree. Okay, I told you that the output of semantic analyzer, that is a annotated syntax tree. So annotated syntax tree means in the syntax tree, basically this semantic analyzer can add some information, like the type information we can add. Okay, so let's read this. You can see that this semantic analyzer, it will gather type information and it will save this information in the symbol table or in the syntax tree for subsequent use during the intermediate code generation. After the semantic analysis phase, we have many other phases. For example, we have the next phase, that is intermediate code generation. So you can see in this intermediate code generation also, this type information will be used, and this type information, this is stored in the symbol table by semantic analyzer. Okay, and I told you that a very important part of semantic analysis, that is type checking. Type checking, what it means? It means that the operator must have matching operands. For example, if you are performing the addition, then you must perform the addition of integer or float, but you should not perform the addition of integer comma string. Okay, so you can see that an important part of semantic analysis, for this semantic analyzer, an important part is basically very important part, that is type checking, where the compiler will check that each operator has matching operands. For example, many programming language definitions, they require that array index to be integer. You can see in many programming languages, for example C language, in the C language you can see the array index must be integer. So the compiler must report an error if a floating point number is used to index the array. Okay, very simple. So let's understand this point. I'm saying that an important part of semantic analysis is type checking, where the compiler will check that each operator has matching operand. Now, this one example is given to you, that in many programming languages, for example in the C language, when you have array, now this array index must be an integer. So you can see that in many programming languages, we require that array index must be an integer. Okay, if you have array A, let's assume, then this array index means this AI. Okay, means this I. For example, this can be 0, this can be 1, this can be 2, like that. Okay, so you can see if you have this array, then this index must be a integer. Okay, if you are writing, if this A is array, this can be integer array, character array, this can be any array, this can be any type of array, but remember the index must always be an integer. Okay, this index, for example A0, A1, A2, so this index must always be integer. Now if this I is floating point number, if you are declaring this I as floating point number, then remember the compiler will report an error. Okay, very simple. I hope you understood. So this is also related to type checking. Okay, I hope you understood. Very simple. Let's see one more task of semantic analyzer. I already told you that an important part of semantic analysis, that is type checking. Now also let me tell you that the semantic analyzer, it will also perform type conversion if the programming language allows. For example, consider this example of C language. In the C language, let's assume x comma y. You can see x is declared as integer variable, and you can see y, the data type of y, that is float. So in the C language, if you write this statement, y, in y we are assigning x plus 3.5. So you can see that this x, this is integer, this 3.5, this is float, integer plus float. Okay, integer plus real number, or I can say integer plus float. So what the C language will do, the C compiler, what it will do, it will implicitly convert this x from integer to float. Okay, this happens in the C language, means the C language allows this type of type conversion, where if you are performing some arithmetic operation on integer comma float, then this integer will implicitly be converted to float. Okay, so you can see this type of type conversion is allowed in the C language. So who will do this type conversion in the compiler? Which phase of the compiler will perform this type conversion? The answer is semantic analyzer. So you can see the semantic analyzer, it can perform type conversions if the source programming language permits some type conversion. For example, I gave you one example of type conversion in the C language. Remember, in the C language also, if you are adding integer comma string, then that is not allowed. Okay, there we cannot do any type conversion. But if you are adding integer comma float, then the C language, or I can say the C compiler, will implicitly convert this integer to float. Okay, so this also will be done. I can say this type conversion, it is also called coercions. Okay, so this type of type conversions, or I can say coercions, these are also performed by semantic analyzer. I hope you understood. So you can read this here. The language specification may permit some type conversions called coercions. For example, if you are performing an arithmetic operation between two integers, two floating numbers, then that is fine. There is no problem. But if you are performing arithmetic operation, if the arithmetic operator is applied to a floating point number and an integer, then the compiler may convert or coerce the integer into floating point number. Okay, so you can see this this type of type conversion, or I can say this type of coercions, these also will be performed. These also will be done by the semantic analyzer. In the semantic analyzer, the type checker will do this. Okay, so you can see the type checker in the semantic analyzer will perform such type of conversions. I hope you understood. Okay, now let's study static semantics versus dynamic semantics. Let me tell you some semantic properties we can check at the compile time, and some semantic properties we can check only at the runtime. So static means that at the compile time we can do this. Compiler can do this. From the source text, we can do this type of analysis. This static semantic analysis we can perform from the source text. Means the compiler can do this static semantic analysis. And what is the meaning of dynamic semantic? Means those semantic properties, those semantic rules which we can check only at the runtime, not at the compile time. So these are called dynamic semantics. Okay, let's study them in the detailed way. So you can see static semantics versus dynamic semantics. Let me tell you, when you study syntax errors, or I can say syntax rules, then all the syntax rules, they are detected by the compiler at the compile time. Okay, means the syntax analysis, all the syntax related analysis, that is done before execution by the compiler. But what about the semantic error? So the semantic error, let me tell you, these semantic errors can be detected by compiler at the compile time. Then these semantic errors will be called static semantics. Those semantic errors which compiler can detect at the compile time by looking at the source text only without running the program. So those semantic errors will be called static semantic error. And there are some semantic errors which we can detect only at the runtime, not by the compiler, of course, because when you are running the program, then already the compilation is over. So these dynamic semantics, I can say these dynamic semantic errors, which we can detect only at the runtime when the program is executing, only at that time we can detect these dynamic semantic errors. So these dynamic semantic errors will not be detected by compiler. These will be detected by the runtime, or I can say at the runtime we can detect them. But let me tell you one thing here. It is not important for us, but let me tell you, actually the compiler cannot detect the dynamic semantic error, because these errors we can only detect when the program is running. I will give you some examples, don't worry. So you can see when the program is actually running, then only we can detect these type of semantic errors. So the compiler cannot detect, very simple, compiler cannot detect these dynamic semantic errors, but the compiler can help the runtime environment, or I can say the compiler can help that at the runtime we can catch these semantic errors. Okay, how the compiler will do that, that of course we don't have to study. But what the compiler can do, in your program the compiler can add some extra text. Okay, so that when you are running the program, then that text, that that code added by the compiler, using that code at the runtime when you are running the program, you can catch, you can detect these dynamic semantic errors. Okay, so very simple point, the compiler cannot detect the dynamic semantic errors, because these errors we can detect only while you are running the program. But what the compiler can do, compiler can add a, a code basically. Okay, whatever type of dynamic semantic error you want to detect at the runtime, let's assume there are 5 or 10 types of dynamic semantic errors you want to detect. Then what the compiler can do, in your source text, in your source program, the compiler can add code, the compiler can add some code. Okay, and using that code at the runtime when you are running the program, then you can detect these dynamic semantic errors. Okay, I hope you understood. So very simple, remember the semantic errors, some of them we can detect at the compile time by the compiler. We will call them static semantic errors, or I can say static semantic rules. And some semantic errors we can detect only at the runtime when the program is executing. These are called dynamic semantic errors, or I can say dynamic semantic rules, and these are not detected by compiler. So you can see, to detect semantic errors, either you can detect at the compile time by the compiler, or at the runtime when you are executing the program. So you can see, compiler or runtime, they will detect the semantic errors. I hope you understood. Very simple. Now let's see some examples of static semantics. What is static semantics? These are the semantic rules. Semantic rules means meaning related rules. Okay, semantic, this means meaning. So you can see, static semantics are the semantic rules of a program that can be checked without executing the program by compiler at compile time. So you can see, these static semantics, these are the semantic rules, these are the semantic properties which compiler can detect, which compiler can check, which compiler can verify at the compile time without executing the program. So remember, these static semantic rules, these static semantic properties, they depend only on the program text, on the types, on the declarations, on the scopes. Basically, I can say that they only depend on the program text. You don't have to execute the program to detect, to verify, to check these static semantic properties, static semantic rules. Okay, so they depend only on program text, and in the program text, for example, types, declaration, scopes, etc. Hence, they are checked by the compiler in the compiler, they are checked by the semantic analyzer. Okay, let's see some examples of static semantics. For example, variable must be declared before use. If you want to verify this property, then of course you don't have to run the program. You can just look at the program text, and in the program text you can see that if you are using a variable, then before using this variable, did we declare this variable? Okay, so you can see that variable must be declared before use. This is a static semantics, or I can say static semantic property, because this is a semantic rule. This is a semantic rule which compiler at the compile time can check, okay, without executing the program. Okay, so you can see this is one property in the static semantic properties. Variable must be declared before use. Another, type compatibility in the expressions. Of course, in the source program, in the source text, you can check that in every expression you have type compatibility, or I can say type matching. Okay, next you can see function call parameter types and parameter count, they must match with the function declaration. Okay, when you are calling the function, then the count of the parameters, also the types of the parameters, they must match with the function declaration. So these things we can check at the compile time. So these are static semantic properties or static semantic rules. For example, consider this example. Here you can see x is an integer variable. We are declaring x as int. You can see here in x we are assigning a string. So x is basically declared as int, and you are assigning a string to x. So this is basically semantic error. I can say static semantic error. Okay, type mismatch. Okay, this has to do with type compatibility in the expression. So in this expression, that there is type mismatch. Very simple. Okay, so you can see this is static semantic error. I hope you understood. Very simple. Now let's see what is dynamic semantics. Dynamic semantics, they describe the meaning of a program during execution. Remember, dynamic semantics, these are the semantic rules, these are the semantic properties which we can detect only when the program is actually running, when the program is actually executing. Then these dynamic semantic rules, these dynamic semantic properties, we can check, we can verify. So at the compile time, before executing the program, at the compile time, these dynamic semantic rules, these dynamic semantic properties, we cannot verify, we cannot check. So the compiler cannot check the dynamic semantics. Very simple. Okay, so you can see dynamic semantics, they describe the meaning of a program during execution. Means what the program actually does when it actually runs. Okay, now they will depend on what? They will depend on runtime values. Means when the program is actually executing, then at runtime, what are the values that are being calculated? What are the values that are being computed? So you can see runtime values to the variables, execution paths, etc. So basically, these dynamic semantic properties, these dynamic semantics, they depend on runtime basically. Okay, very simple. I hope you understood. Now let's see some examples. These are the examples of dynamic semantics. Means these actually we cannot verify at the compile time. Without running the program, these semantic properties, these semantic rules, we cannot verify, we cannot check, the compiler cannot check. For example, I told you this division by zero. Let me tell you, I told you that this division by zero is actually not a syntax property, it is actually a semantic property. Okay, now let me tell you, in the semantic property also, this is basically dynamic semantic property. Means division by zero, this actually we cannot detect at the compile time. At the runtime, when the program is actually running, then this error can come. This this divide by zero error can come. For example, let's assume in your program you have this statement a. In a we are assigning 5 divided by b. Now you can see at the compile time, we don't know the value of b. Yes or no? Maybe there is a loop. In that loop, maybe the variable b is changing. Okay, yes or no? So only at the runtime, it can happen that at the runtime when the program is executing, then it can happen, maybe there is a loop and the b is changing, b is changing, b is changing, and then b becomes 0. Then you can see at the runtime when the program is actually executing, then you can see that this type of error can come, that division by 0. So you can see this is basically dynamic semantics, means this we can verify, this we can check only when the program is running. Without running the program, if you have this statement in your program, then at the compile time, how can you check this? Okay, because at the compile time we do not know what will be the value of b when you run the program. Yes or no? I hope you understood. So you can see that this division by 0 and this example I gave you, this is basically one example of dynamic semantics. Another is array index out of bounds. For example, in your source program, let's assume you have this statement, these statements you have, that this a is array of integer type. You can see this a is integer array, and the size, you can see size is 5, means the index can be a0, a1, a2, a3, a4. Yes or no? So you can see that this is an integer array of size 5. Okay, now let's assume in our source program we have this statement ai equal to 10. Now you can see that at the compile time, without running the program, before executing the program, at the compile time we don't know the value of I, because when you actually execute the program, then what can happen? Maybe this I will change, maybe there is a loop, and maybe this I is changing, I is becoming 0, then 1. That is fine. Okay, if I is becoming 0, I is becoming 1, I is becoming 2, that is fine, because this a is an integer array of size 5. Okay, so basically from a0 to a4 everything is fine. But let's assume that some loop is there. Okay, and let's assume this I becomes 7, this I becomes 10. Then you can see that there will be error, that is array index out of bounds. Okay, this error will be there. So you can see that this error we are detecting only when the program is actually running. When the program is in the execution, then we can detect, then we can verify, then we can check this error. So this is called dynamic semantics, or I can say dynamic semantic property, dynamic semantic rule. I hope you understood. Okay, there are some more dynamic semantic rules which we can detect only when the program is actually executing. For example, stack overflow. Stack overflow, this we can detect only when the program is actually executing. Okay, yes or no? For example, arithmetic overflow. Maybe in your program, in your source program, maybe you have a plus b, where a is integer, where b is integer. These are fine. But maybe the value of a is very big, the value of b is very big. Let's assume in the, if you have integer variable, and let's assume the size of int is something, and let's assume the maximum value that we can store here, let's assume for a moment, let's assume that is 50,000. Okay, I'm assuming that in the integer variable, this is the maximum value we can store, let's assume. Okay, now let's assume that at the runtime, what can happen? This statement you have in the source program, but at the runtime, what can happen? Maybe this a value has become, let's assume 49,000, and this b value has become, let's assume 5,000. So now you can see that this is perfectly fine. A 49,000, b 5,000, these are perfectly fine. But remember, if you do the addition, then what will happen? The result you cannot store, the result you cannot store here. Okay, because the maximum value that I can store in an integer is basically arithmetic overflow. So you can see these are the some of the examples of dynamic semantics. Means these properties, these semantic rules, these semantic properties we cannot verify at the compile time. These we can only verify, these we can only check when the program is actually in the execution, when the program is actually running, then only we can check, we can verify these properties. So these properties, these semantic rules cannot be detected, or I can say these cannot be verified, these cannot be checked by the compiler, but these will be checked by the runtime. I hope you understood. Okay, very simple. So let's see some examples here. You can see, consider a main program here, and there is a dot prod, this dot product, this function is there. Okay, so you can see this is a function declaration. You can see in this function declaration, basically this dot product, this function, you can see the return type, that is integer, and there are two arguments, and both the arguments are basically array. Okay, both the arguments are array. Okay, now you can see here what are the static semantics that we can check. Okay, so you can see some samples of static semantic checks in the main function. In this main function, what are the static semantic properties that we can check? Okay, is this clear? You can see here what is written. Let me tell you, these are basically samples of static semantic properties, static semantic rules that we can check in the main function by the compiler. Compiler can check, for example, the type of p and the return type of dot product should match. You can see here that this p, this is of integer type, and in this p we are assigning the return value of dot product function. Okay, so you can see the return type of this dot product, that is basically integer. So in integer variable you are assigning integer value, so it is perfectly fine. Yes or no? So you can see that type of p and the return type of dot prod should match. Yes, that is matching. Okay, this is called type matching. Yes or no? Very simple. Now let's see the next. You can see the number of parameters and the type of parameters of dot prod are same in its declaration and call. So here you can see that we are calling this dot product function. Okay, in the main function we are calling this dot product function, and you can see we are passing two parameters. So you can see the number of parameters is perfectly fine. Okay, you can see in the function declaration also we have this dot product function has two parameters, and in the function call also we are passing two parameters. So you can see the number of parameters is perfectly fine. Also, what about the type of parameters? You can see in this dot product function the two parameters are basically array. Okay, these are basically integer array. Both the parameters are integer array, and you can see what we are passing. We are also passing integer array. This a comma b, these are integer arrays. So you can see that the number of parameters and also the type of parameters of dot prod are same in both its declaration and its use, or I can say in its call. Okay, here you are calling the function, or I can say you are using the function, and here this is the function declaration. So the number of parameters and also the type of parameters, they must match. Okay, very simple. Now you can see the next is p is declared before use, same for a comma b. You can see here you are using p, but before that p is declared in the main function. Also you can see that here we are using a comma b, and here they are declared. Okay, so you can see a comma b, p, all these are declared before we are using them. Okay, I hope you understood. So these are the static semantic properties that we can check in the main function. Okay, very simple. Now consider this example. Here the dot product function, that is same. Okay, in the previous slide you can see this dot product function, this is same basically. Okay, this is as it is. That is the reason this is not written fully. It is same as the previous slide, but here the main function we have changed. Okay, now you can see in the main function we have integer array a, we have integer array b, then you have printf dot product, we are calling dot product, this function you are calling dot product, this function you are calling, and here you can see this p is a integer array. This p again, this p is not an integer variable, this p is basically integer array, and in this p you are assigning the return value from dot product. Okay, and here you can see printf %dp. So let's see what are the semantic errors that we will get here in this main function. In the function main, what are the semantic errors we are going to get? Actually many semantic errors we will get. For example, look at the line 3 in the main function. In the main function at the line 3 you can see that we are calling this dot product function, but we are passing only one parameter. But remember, in the function declaration the dot product function is expecting two parameters. We are passing one parameter only. Okay, so you can see we got a semantic error. we got static semantic error. So you can see this static semantic error, we got too few arguments to the function dot product. Okay, these errors actually will be given by the GCC compiler. Okay, you can read this here, that these are the errors given by the GCC compiler. Okay, this is a C language program. If you write this type of C language program, then these semantic errors will be given by the GCC compiler. Okay, so you can see at the line 3, this error you will get, this static semantic error you will get, that too few arguments to the function dot product. In when you are calling the function dot product, then we are only providing only one argument, but actually the dot product declaration, this function declaration, has basically two arguments. Okay, two parameters. Now you can see the next on the line number 4, you can see you are calling this dot product function, and in this function call we are passing 3 parameters, but actually the dot product function, it is expecting only 2 parameters, so I can say too many arguments. So at the line 4, we will get static semantic error, too many arguments to this function called dot product. Okay, next you can see that in this P we are assigning the return value of dot product function. Now you can see that this P is actually integer array, and what the return type of dot product, that is integer. So remember, the dot product function, it will return integer value, and that integer value we are assigning to array. Okay, to the array name. So you can see this is the array name. Okay, so you can see that this integer value you are assigning to the array name, that is also static semantic error type mismatch. Okay, yes or no? So you can see error in the line number 5, there is error, that is incompatible types in the assignment. Okay, very simple. Of course, there is another error here. You can see type mismatch error is there here. You can see this %dp. This %d, this is expecting integer. Okay, but you can see what is this p? This p is array. So you can see here, this is another error, or I can say warning, that this %d format %d expects type int, but what we are providing? We are providing int star. You can see this p, this is an array. So here in this error, or I can say in this warning message, they are writing that the type is int star. Okay, but actually this %d, this is expecting, this expect type int. Okay, so I hope you understood. I hope this has become very clear. What are semantic errors? What are semantic properties? What are static semantic properties, dynamic semantic properties? Okay, I hope these things have become very clear. Let's see some more. You can see in this dot product function, what are the static semantic properties we can verify, we can check. Okay, already we have already seen that in this main function, what are the static semantic properties that we can check, we can verify. Now let's see that in this dot product function, what are the static semantic properties, static semantic rules that we can check, we can verify. Okay, for example, you can see d comma I, these are declared before we use them. You can see here d comma I, here they are declared, and here we are using d, here we are using I. So you can see before we use d, we have already declared. Before we use I, we have already declared. Okay, so you can see this is perfectly fine. Okay, next you can see type of d matches the return type of dot product. Okay, so you can see here the return d. Okay, we are returning d. So in this dot product function, focus on this dot product function. What we are returning? We are returning d. But actually, this dot product function is saying that the return type is integer, and we are returning d. So definitely d must be integer. Yes or no? Notice one thing, that the dot product function, it is saying that the return type is integer. I will return integer value. But you can see inside this dot product function, what actually we are returning? We are returning d. So this d must be integer. Yes or no? So you can see that type of d matches the return type of dot product. Yes. Next you can see type of d matches the result type of star. You can see here. Okay, this d, basically what this actually means, this means d equal to this statement, actually what this means, so it actually means d equal to d plus xi star yi. Okay, this is what it means. Now you can see what we are saying. We are saying that type of d, okay, here type of d that matches the result type of star. Okay, so you can see here the result that will be produced, the type of that result matches the type of d. Okay, because you can see here what will be the type of result of this star. This star is multiplication. You can see what is this xi. You can see this x is an integer array, y is an integer array. So what is an element of array? What is an element of integer array? That is integer. Yes or no? So very simple point. I am saying that x is integer array, y is integer array. And what is xi? This is an element of integer array. So this is integer, this is integer, integer multiplied by integer, that is integer. Okay, so here you can see the result of star, that is integer. The result of star, that is integer. And you can see now we are adding d with integer. Okay, this d we are adding to integer. So you can see the type of d matches the result type of star. Okay, means basically this type of d matches integer. Yes, because the type of d, that is integer. So yes, that is also correct. Okay, next you can see the elements of arrays x comma y are compatible with the star. Yes, because the elements of array x comma y, the elements of array x comma y, these are integers. So yes, they are compatible with star. Okay, integer multiplied by integer we can do, but we cannot do string multiplied by string. Yes or no? Multiplication cannot be performed for strings. So you can see that elements of array x comma y, the elements of array x comma y, these are integers. So they are compatible with star. Okay, so these are the static semantics, or I can say these are the static semantic properties that we can check in the dot product function. So what we have seen what are the static semantic properties that we can check for main function, what are the static semantic properties that we can check for the dot product function, and also we have seen some static semantic errors which can be caught by the compiler at the compile time without running the program, without executing the program. I hope you understood. Now let's see some examples of dynamic semantics. Okay, I told you some examples of dynamic semantics. For example, divide by zero, array out of bounds, stack overflow, arithmetic overflow. These are some examples of dynamic semantics. And dynamic semantics, what that means? That means that these semantic properties we cannot check, we cannot verify at the compile time without running the program, without executing the program. Basically, we cannot check these properties, these semantic rules, these semantic properties. Okay, so here you can see some examples here. The samples of dynamic semantics checks in dot prod. Okay, so some examples are given here. Basically, some samples of dynamic semantic rules, dynamic semantic properties that we can check in the dot product function. So what are those? For example, this I, you can see here we are writing in the source program, we are writing xi. So basically we need to check that at the runtime this I value must not go out of array bounds. Okay, you can see what is the array size. You can see in the main function, when you call this dot product function from the main function, at the runtime what will happen? At the runtime, first this main function will start executing. In this main function, when you call this dot product function, then these arrays, you can see a comma b, these are integer arrays, these we are passing. Okay, so you can see this x comma y, these are basically a comma b. Yes or no? This a we are passing to x, this b we are passing to y. Okay, so you can see the size of x comma y, these are basically 10. The size of array x, the size of array y, these are 10. So you can see that we must verify, we must check that at the runtime this variable I, it should not become negative. Also, it should not become greater than or equal to 10. Okay, yes or no? Because this I can be 0 to 9. Yes or no? This index can be 0 to 9 because the size of array that is 10. The size of array x, the size of array y, that is basically 10. So remember, we need to make sure that at the runtime, this will not become a value greater than equal to 10. Okay, and actually you can easily see here that this I value, if you notice, this is starting from 0, I plus plus, I less than 10. So you can see that actually I value will never become greater than or equal to 10. Okay, yes or no? So definitely at the runtime, there is no problem of array out of bounds. Okay, but the point is that this array out of bounds, this semantic property, we can check only while running the program. When the program is actually running, then only we can check it. Okay, because when the program is actually running, then we get to know what is the value of I, this variable I, what the values it will take. Okay, yes or no? In this source program at the compile time, we cannot find what are the values this variable I will take. Yes or no? When the program is executing, then what are the values that this variable I will take? These we cannot find at the compile time. Only at the runtime, when the program is actually running, then only we can find what are the values this variable I can take. Okay, yes or no? So you can see that values of I value of I value of I does not exceed the declared range of array x and y, both lower and upper. Lower and upper means lower bound, that is basically 0. Okay, here you have array size 10, array x, array y, they have size 10. So what is the lower range? That is basically 0. The index can be 0. So I can be 0, that is perfectly fine. The upper range, that is basically 9. So I can be maximum 9. Okay, I can be from 0 to 9, that is fine. But I should not be negative. I should not be more than 9. Okay, very simple. Now let's see the next, that is there are no overflows during the operation star and plus in when you are performing this statement, when you are executing this statement, then here you are basically what you are doing d equal to d plus xi into yi. Now you can see that it should not happen that at the runtime, when you are running this program at the runtime, it should not happen that when you calculate this value, this multiplication when you calculate, or this addition when you calculate, then it should not happen that the result becomes bigger than what we can store in the integer. Okay, yes or no? It should not happen at the runtime. It should not happen that this result becomes bigger than what we can store in the integer variable. Okay, I hope you understood. So basically that there should be no overflow. And again, of course, this we can check only when the program is running, because when the program is not running at the compile time, we don't know what the value this xi will take, what the value this yi will take, what the value this d will take, what the value this addition will give. Okay, yes or no? So these things, of course, we don't know at the compile time. When the program is actually running, only at that time we will get to know about these computations. Okay, so you can see that these are dynamic semantic checks, or I can say dynamic semantic properties that we can check only at the runtime when the program is actually running. Okay, I hope you understood. So you can see arithmetic overflow, array out of bounds, and of course some more example. For example, stack overflow. Okay, you can see stack overflow. So stack overflow, arithmetic overflow, array out of bounds, divide by 0. These are some examples of dynamic semantic checks. Okay, I hope you understood. Here you can consider this example where we have this factorial function. We are finding factorial of n factorial we are finding. So you can see this is a recursive function. Here what we are doing, here you can see this factorial fact n, it will call fact n minus 1, it will call fact n minus 2, it will call fact n minus 3, and so on. Okay, so you can see, for example, if this n value is 10, then you can see first we will call fact 10. Okay, notice, you can see we are calling from the main function. Okay, focus here. From the main function, you can see this p is an integer. P is integer, and in this p we are assigning the return value from this fact 10. So of course, one thing you notice, static semantic check. What is that? One static semantic check is that this type of p, it should match with the return type of fact 10, with the return type of this fact function. Yes, the return type of this fact function, that is integer, and this p is integer, so yes, they are matching. Okay, so here basically they are, the type matching is there. Okay, basically types are matching. Also you can notice that this p we are using here, so this p is declared before use. So of course these are basically the static semantic checks. Okay, these are static semantic rules, static semantic checks. But what are the dynamic semantic checks? So you can see that from the main function, we are calling this fact 10. So first we call this fact 10. This fact 10, what it will do, it will call fact 9, then fact 8, fact 7, and so on. So what will happen? In the stack total, you can see fact 10, then fact 9, and so on. So you can see that in the stack, 10 activation records will be inserted. Okay, yes or no? Of course, 10 is not a big value. So because of 10, because of n equal to 10, of course, we will not get this stack overflow error. We will not get. But if this n value is, let's assume, bigger, okay, if this n value is a big value, then of course, if you are finding the factorial of a big value, then of course what can happen at the runtime when you are running this program, at the runtime it can happen that stack overflow error can come. Okay, stack can overflow. So you can see that stack overflow, that is also a dynamic semantic check. Okay, only at the runtime when the program is actually running, only at that time we can check for stack overflow. Okay, yes or no? So very simple. And of course, arithmetic overflow. Okay, arithmetic overflow, you can see when you multiply this, then it should not happen that, let's assume that this n value, here you are calling, you can see, let's assume this n value is a big value. For example, let's assume 1000. Okay, now let me tell you what will happen. This 1000 factorial will actually be a very big value. Okay, you can see, if you see 5 factorial, that is 120. If you see 6 factorial, that is 720. Okay, forget about 1000. Even if this is, let's assume, 100. Okay, n equal to 100, it doesn't seem like a big value. N equal to 100, this does not seem like a big value, but this 100 factorial is a very big value. Yes or no? So you can see that, let's assume, in the main program you are calling fact 100. Let's assume, okay, in the main program you are calling fact 100. Now of course, it, to us right now, it doesn't seem like a big value. We are just calling fact 100. But what will happen? It will happen that this fact 100 we are calling, then 100 multiplied by fact 99, then 100 multiplied by 99 multiplied by fact 98. Okay, and so on. So you can see this fact 100 will actually become a very big value. So it may happen that when you perform this multiplication, then it may happen that there is arithmetic overflow. Okay, means the result of this multiplication, the result we cannot store in a integer location. Okay, I hope you understood this point. So I hope all these points are very clear. I hope it is clear what are the semantic rules, what are static semantic rules. Okay, basically the semantic rules, static semantic rules, dynamic semantic rules. Okay, I hope all these points are clear. Also, the semantic rules, the syntax rules, the syntax errors, the semantic errors. Okay, I hope everything is clear. The work of semantic analyzer, I hope all these things are clear. Okay. This we have already seen that what this semantic analyzer will do. It will store the type information in the symbol table or in the syntax tree. This actually we have already discussed. Okay. So what are the different works that the semantic analyzer will do? All those things we have already discussed. Okay. So you can see that type information is stored in the symbol table or in the syntax tree. For example, type of variables, function parameters, array dimension. Okay. So all these things, these can be stored in the symbol table by the semantic analyzer. Of course, remember, once these informations about basically the type information, once it is stored in the symbol table, then the subsequent phases of the compilation, for example, intermediate code generator and the other phases like optimizer. Okay, so you can see that the subsequent phases of the compilation, they can also use this information. Okay, so you can see that this type information means type of variables, function parameters, type of functions, function parameters basically. Okay, so you can see array dimensions. All this information is stored in the symbol table by the semantic analyzer, and not only semantic analyzer, but actually the subsequent phases of the compilation, they will also use this information. I hope you understood. So this is the summary of whatever we have seen so far. So far we have seen what is the meaning of semantic analysis, what the semantic analyzer will do. So you can read this quickly. So you can see semantic consistency that cannot be handled at the parsing stage is handled here. You can see parser cannot handle context sensitive features of the programming languages. But in the analyzer, or I can say in the semantic analysis phase, we can handle the context sensitive features of the programming languages. Okay, we will see actually one example I will show you in this lecture. I will show you a very beautiful example. From that example, you will actually understand the meaning here. Okay, so you can see that parsers cannot handle context sensitive features of the programming languages. So semantic analyzer, it can handle, or I can say in the semantic analysis phase, we can handle. Okay, next you can see, I told you that there are two type of semantic properties: static semantic properties that we can check at the compile time, dynamic semantic properties that we can check only at the runtime. So you can see that these are the static semantic properties. So you can see these are the static semantic properties of the programming languages, and these can be checked by the semantic analyzer, means by the compiler. Okay, so you can read this, that variables are declared before use. Next you can see type match on both sides of assignment. Parameters type and the number of parameters must match in the declaration and use. Okay, so like this, these are the static semantic properties of programming languages which can be checked by the semantic analyzer. Now these are the dynamic semantic properties of the programming languages which we can check only at the runtime, so the compiler cannot check. But I told you one thing, that compiler can generate code which will help to check these properties at the runtime. Okay, I hope you understood this point. So remember, compiler cannot check the dynamic semantic properties of the programming languages, because these dynamic semantic properties of the programming languages, these we can check only at the runtime when the program is actually running. Okay, so the compiler cannot check them. But what the compiler can do, compiler can generate code in your program. Compiler can add some pieces of code, compiler can add, so that at the runtime we can check these properties. Okay, these dynamic semantic properties we can check. I hope you understood this point. So basically, compiler cannot check, but the compiler will be helpful. I can say compiler will help the runtime. Okay, very simple. I hope you understood. So you can see whether an overflow occur during arithmetic operation, means arithmetic overflow, does it occur at the runtime, does it occur? Okay, so you can see whether array limits will be crossed during execution, whether recursion will cross stack limits, means stack overflow, whether heap memory will be insufficient. So basically these are some examples of dynamic semantic properties of programming languages which we can check only at the runtime, not at the compile time, not by the compiler. Okay, I hope you understood. This is the complete summary of whatever we have seen so far. Okay, now let's discuss how the compiler will do static semantic analysis. Remember, the compiler cannot do dynamic semantic analysis, that we have already seen. The dynamic semantic properties of programming languages, compiler cannot check. Okay, so you can see, when we say that compiler does semantic analysis, then basically we are saying that this compiler does static semantic analysis. Okay, so from now onwards, whatever we will study, whatever semantic analysis we will do, that is basically static semantic analysis. Okay, so you can see that compiler will do static semantic analysis. Compiler cannot do dynamic semantic analysis, that we have already seen. Now, how does the compiler do static semantic analysis? This is important. Okay, now you recall one thing, how the syntax analyzer will do the syntax analysis. Just recall this point. The syntax analyzer, or I can say the parser, how it will do the syntax analysis? It will use context-free grammars, correct? Yes or no? So you can see that for specifying the syntax of a programming language, to specify the syntax of a programming language, we use context-free grammars. So the syntax analyzer, or I can say the parser, it will use context-free grammar to perform syntax analysis. Yes or no? Very simple point. So you can see that context-free grammars are usually used for syntax specification of programming languages. So what the syntax analyzer will do? It will use context-free grammar to perform syntax analysis. Now you can see the syntax analyzer is using context-free grammar to perform the syntax analysis. Similarly, the semantic analyzer will use SDT or SDD to perform semantic analysis. Okay, so let me tell you this point here. You can see the parser will perform syntax analysis. Parser means syntax analyzer. So the parser will perform syntax analysis using context-free grammar. Similarly, remember the semantic analyzer, it will perform semantic analysis using SDT or SDD. These are two different concepts. We will see one by one. In this lecture, we will study this SDT in a very detailed way with all the GATE PYQs. In the next lecture, we will study SDD. These are different concepts, remember. Of course, they are related to each other. We will see how they are related to each other in the next lecture when we study SDD. But right now, just understand that these are two different notations, or I can say two different concepts. Okay, so very simple point. So you can see that the parser will perform the syntax analysis using context-free grammar. Similarly, the semantic analyzer will perform semantic analysis using SDT or SDD. I hope you understood. Okay, so you can read this that the parser will perform syntax analysis using context-free grammar CFG, and the semantic analyzer will perform semantic analysis using SDT or SDD. What is SDT? The full form is syntax directed translation. And what is SDD? This is syntax directed definition. These are different concepts. They are related to each other, but they are different concepts. Okay, or I can say they are different notations. I hope you understood. So you can see, for example, this context free grammar. This is a notation used by parser. Similarly, this SDD, SDT, these are notations used by semantic analyzer. I hope you understood this. Okay, so you can see that the semantic analysis is what we want to do. The compiler want to do semantic analysis. But to do this semantic analysis, the compiler will use SDT or SDD. So you can read this that semantic analysis is what the compiler want to do. And SDT, SDD, these are how the compiler will do it. Okay, means, for example, if you want to do syntax analysis, then you will use this tool, this context-free grammar. This is a tool. This is a notation. This tool you can use to perform syntax analysis. Similarly, SDT, SDD, these are also tool. Okay, similar to context-free grammar. Similar to context-free grammar, these are also tool. These are also notations. These are also mechanisms using which we can perform semantic analysis. I hope you understood. Okay, so you can see this that SDT, SDD, they are different concepts, and what they will define, let me tell you, they will define what the semantic information we want to compute. Okay, what is the semantic information you want to compute? Static semantic check you want to perform. Which static semantic check you want to perform? Okay, so that you can define using SDT or SDD. Okay, again I'm telling you very simple point. Understand this. There are different types of static semantic checks. We have already seen. For example, variables should be declared before it is used. Okay. For example, type mismatch should not happen. Okay. Type must match. Okay. And for example, you can see in the function call, the number of parameters and the type of parameters, they must match the function signature, or I can say the function declaration. So these are some examples of static semantic checks. Now, which static semantic check you want to perform? Which static semantic information you want to compute? That you can define using SDT or SDD. Okay, very simple. And what this semantic analyzer will do? It will perform this semantic analysis using SDT or SDD. I hope you understood. So let's see this note. From this note, you will feel more confidence about SDT, SDD. So let's see this. You can see here for lexical analysis, which is the tool that we use to perform lexical analysis. The lexical analyzer will use which mechanism, or I can say which tool, or I can say which specification? That is regular expression. Very simple. To perform syntax analysis, the parser will use which tool? The syntax analyzer will use which tool, which formal mechanism, or I can say which specification we will use? That is context-free grammar. Similarly, for semantic analysis, which tool we will use, which formal mechanism we will use, or I can say which specification we will use to perform semantic analysis, that is SDT or SDD. I hope you understood. Okay, very simple. So you can read this, whatever we have seen so far, that is written here. This is the summary basically. So you can see semantic analysis computes additional information related to the meaning of the program once the syntactic structure is known. Means once the syntax analysis is done, in the syntax analysis, the parser will check for the syntactic structure. Yes or no? Valid syntactic structure. So you can see once the syntax analysis is done, then the output of syntax analyzer, that is parse tree, that parse tree will be input to the semantic analyzer. And what the semantic analyzer will do? It will compute additional information related to the meaning of the program. Okay, you can see in the language like C, the semantic analyzer, what it will do? It will also add information, type information. I told you, type of a variable, the parameter informations, or I can say the array dimensions. Okay, so you can see that in the language like C, the semantic analyzer, what it will do? It will add information to the symbol table, and also it will perform type checking. Okay, this we have already seen. So you can see that these things like type checking, okay, these things like type checking, these are actually beyond the capability of context free grammar. These are beyond the capability of parser, or I can say syntax analyzer. Okay, so that is the reason these checks, these meaning related checks, we have to perform in the semantic analysis phase. Okay, very simple. And you can see here, like we have already seen that for this lexical analysis, for this syntax analysis, we have used representation formalism. What is the representation formalism? For example, for lexical analysis, this representation formalism we have used, or I can say this representation we have used, that is regular expression. For syntax analysis, we have used this tool or this mechanism, that is context free grammar. Now for semantic analysis, we use SDT or SDD. Okay, so you can see here that for semantic analysis, we use syntax directed translation or syntax directed definition, SDT or SDD. Okay, I hope you understood. Now we will see the general idea of syntax directed translation. Okay, so now I am going to explain you the idea behind this syntax directed translation. Once you understand this idea, then SDT, SDD both will become very easy. Okay, and this is very intuitive idea, so let's understand this. The idea behind syntax directed translation, that is actually very easy. With help of example, we will try to understand this, but let's see what is the idea. So you can see the principle of syntax directed translation. The idea of syntax directed translation, it states that the meaning of an input sequence is related to its syntactic structure, means it is related to parse tree. So this is the idea behind syntax directed translation. Okay, the name itself is telling you, you can see syntax directed translation, or I can say syntax directed semantic analysis, means basically to perform the semantic analysis, that semantic analysis is directed by syntax. Okay, so the name itself is telling you that semantic analysis is directed by syntax. Okay, so you can read this with help of example, it will become very clear what this means. So you can see the principle of syntax directed translation, in short we will call it SDT or SDD also. The same idea for SDD, means syntax directed definition also. So you can see the principle of syntax directed translation states that the meaning of an input sequence, the meaning of an input sequence is related to its syntactic structure, means it is related to its parse tree. Okay, so let's understand with help of an example. So you can see, consider this example. This is a grammar rule, this is a context free grammar rule. E going to E plus E, means expression can be expression plus another expression. Yes or no? Expression plus another expression, that is basically expression. Okay, now you can notice what I can do to perform the semantic analysis. Our purpose is to perform the semantic analysis. Semantic analysis means meaning related analysis. Okay, so what we can do with this grammar production rule, we can attach meaning. Means what is the meaning of this rule? Okay, very simple point. So remember, with this grammar rule, we can attach meaning. Okay, so you can see this meaning I have attached. So you can see this is the grammar rule. Okay, remember this grammar rule both are same, but you can notice what I'm doing. Even E2, E3, these are just to distinguish between this E, this E, this E. Okay, for example, here if I'm talking about E, then which E I'm talking about? Okay, so that is the reason we are using E1, E2, E3, but actually all are basically E. This is also E, this is also E, this is also E, but just to differentiate between them, like which E are we talking about? Okay, so just to differentiate between these different E's in this production rule, so we are using E1, E2, E3 like that. Okay, so you can see this is your grammar rule. With this grammar rule, this meaning we have attached. Okay, this is the meaning of this grammar rule, right? Okay, you can notice in this grammar rule, basically what we are doing, you can see the value of this expression, that will be equal to the value of this expression plus the value of this expression. Yes or no? This is the meaning. Do you agree with me? Okay, when you see this grammar rule, then the meaning, if you notice, that is basically that the value of this expression will be equal to the value of this expression plus the value of this expression. So you can see what we are doing, we are attaching the meaning with the grammar rule. Okay, and this overall, this thing that we are getting, okay, so you can see this object that we are getting, this complete object, remember this complete object that we are getting, this is basically your syntax directed translation. Okay, so very simple point. I hope you understood that with the grammar rule we are attaching the meaning, or I can say this is also called semantic rule or semantic action. Basically this semantic meaning we are attaching, this semantic rule we are attaching, this semantic action we are attaching with this grammar rule. I hope you understood. Okay, so here you can see that this, if you notice, this is called semantic rule. Okay, this is called semantic rule. You can call it semantic rule or you can call it semantic action. Okay, and this is our grammar rule, grammar production rule. Okay, and with the grammar production rule, when we attach this semantic rule, then this complete thing, this complete object, this is basically your syntax directed translation. Okay, it will become more clear as we go on, don't worry. But right now I hope you understood the principle of syntax directed translation. The principle of syntax directed translation basically says that to perform the semantic analysis, the meaning of an input sequence that is related to its syntactic structure. Okay, I hope you understood. So you can see basically that is the reason we are using this name, that syntax directed semantic analysis. Okay, that the syntax is driving the semantic analysis. Okay, and to perform the semantic analysis, of course, what we need to do, we need to attach the meaning with the production rules. Okay, because semantic analysis means meaning related analysis. Okay, so to perform the semantic analysis, the semantic rule, the semantic action, the meaning we have to attach with the grammar production rule. Okay, very simple. Now let's see very interesting example. Actually, I told you one thing, that the parser means syntax analyzer, the syntax analyzer cannot handle the context sensitive features of the programming language. Correct? Okay, because the parser, the syntax analyzer, it uses context free grammar, and the context free grammar cannot represent context sensitive features of the programming language. Okay, so now let me tell you, this semantic analysis, this can handle context sensitive features of the programming language. This I told you, but now I am going to prove to you. Okay, if you remember, just earlier in this lecture I told you this point, that the syntax analyzer, the parser, cannot handle the context sensitive features of the programming languages, because the syntax analyzer is using the context free grammar, and context free grammar cannot represent context sensitive features of the programming language. Okay, but I told you that semantic analysis phase can handle the context sensitive features of the programming language. And now with help of this example we are going to prove to you. Okay, I am going to prove to you. So this is a very beautiful example. Let's just try to understand. Of course, remember, this is just an intro. Remember, So don't worry if you do not understand all the things in this example. I will try that you understand everything in this example because it is very intuitive. Okay, the explanation is also very intuitive. So I think you will understand everything here, what I want to convey. But just in case, if you have any doubt, then don't worry. This is just a intro to the syntax directed translation. Okay, so you can see here, we have this context free grammar, and this context free grammar generates the language a power m, b power n, c power p, m and p greater than equal to 1. Actually, you can easily notice s is going to abc. You can see what this a is generating. A is generating a power m, where m is greater than equal to 1. Okay, so very simple. Next, you can see that this b, what it is generating, it is generating this b. This b is generating b power n, okay, where n is greater than equal to 1. And this c is generating c power p, where p is greater than equal to 1. Okay, and finally, you can see this s is generating abc. So a power m, b power n, c power p. Okay, this is the language generated by this grammar. Okay, now notice one thing. What I'm saying, I'm saying that we can define an attribute grammar. Don't worry about the meaning of this attribute grammar. This will become clear as we go on in the next lecture. When we study SDD, syntax directed definition, there it will become very clear what is attribute grammar. But basically, right now you just understand that we are attaching the meaning to the production rules. Okay, we are attaching semantic rules, semantic actions, the meaning to the production rules. This is how we are getting a attribute grammar. Okay, for example, in the previous example also, you can notice in this example, if you notice here, that this attribute we are attaching with every non-terminal. Okay, you can see this value. Okay, this value attribute is associated with non-terminal e. Okay, with non-terminal e, this value attribute is associated. Okay, so you can see that this expression value e1 dot value, that will be equal to e2 dot e2 dot value plus e3 dot value. Okay, so you can see that what we are doing here, basically, this is your context free grammar production rule, and in this rule what we are doing, we are associating the non-terminals with the attributes. This is one thing. Okay, you can see here that this is, okay, let me write this, that this is basically, this is attribute. Okay, well, attribute well of e. Okay, very simple. I hope you understood. So you can see that what we are doing, we are associating every non-terminal with some attributes. Every non-terminal that is basically associated with some attributes. Also, with this production rule, with this grammar production rule, we are attaching the meaning, the semantic rule, the semantic action. Okay, so the same thing we are going to do here. You can see that the question is saying that, can we define an attribute grammar based on this context free grammar? Based on this context free grammar, can we define an attribute grammar which will generate this language a power n, b power n, c power n? This is very interesting because you already know this a power n, b power n, c power n. This language is actually context sensitive language, not context free language. Yes or no? This language can never be generated by any context free grammar. You can see this language I can never generate with context free grammar. So whatever context free grammar you take, this language you can never generate. But notice one thing here. In this syntax directed translation, we don't just have context free grammar. We have context free grammar plus the meaning. Yes or no? Context free grammar plus semantic rules. Now remember, context free grammar plus semantic rules, this combination is so powerful that you can recognize, you can generate this language a power n, b power n, c power n. Okay, let me prove it to you. But I hope you are understanding the point that this context free grammar plus the semantic rules, okay, this combination is basically very powerful. This combination is basically called syntax directed translation, and using this combination we can handle some context sensitive features of the programming languages. Okay, is this clear? So now what we are going to do with this context free grammar, with this context free grammar, I will attach some semantic rules, and then we will try to generate this language a power n, b power n, c power n, means the count of a equal to count of b equal to count of c. Yes or no? So of course we have to count. We have to count the number of a, number of b, number of c, and the count must be equal. Okay, yes or no? So let's see now what we are going to do. Now let me do it. So you can see here, this is our grammar. Let me write the grammar first. Then with the grammar, I will attach the semantic rules. Okay. And it is very intuitive. You can also do it. Okay. You can also understand it the way I am doing. Okay. So first, let me write all the production rules of the grammar. So you can see in this grammar, we have this production rule S going to ABC. Okay. Next, you can see that A is going to AA. A is going to A. Next, you can see B is going to BB. Okay. You can see B is going to B. Next, C is going to CC and C is going to C. Okay. So these are the production rules of the grammar. Of course, this grammar will generate A power M, B power N, C power P. Okay. But we want to generate A power N, B power N, C power N. And remember, this language is CSL, not CFL. So there is no context free grammar which can ever generate this language. But remember, here what we are doing, here we are not writing the context free grammar, but actually we are writing context free grammar plus semantic rules. Okay. Now let's see what we need to do. One thing is very intuitive. See, just intuitively you understand. If I tell you to recognize this type of strings, A power N, B power N, C power N, where the number of A equal to number of B equal to number of C, basically what you will do, what is the idea? If I want to generate this language, then the idea is that let's count how many A's are generated, how many B's are generated, how many C's are generated. Yes or no? The count of A, count of B, count of C. Let's find it. Yes or no? Let's count the number of A, let's count the number of B, let's count the number of C. Okay. So you just tell me, with this production, what semantic rule I should add? Very intuitive. With this production, in this production, you can see capital C, this non-terminal C, this is going to small c. So how many C's we generated? What is the count of C? That will be basically 1. Yes or no? So you can see that, first of all, notice one thing, that with these non-terminals, I need to count the number of A's, I need to count the number of B's, I need to count the number of C's. So with these non-terminals, with these non-terminals, I will associate an attribute count. Okay, let me associate an attribute count, means C dot count. This count, this attribute I am associating with these non-terminals, okay, to count how many A, how many B, how many C's are generated. So you can see here, with this production rule, which semantic rule I will attach. So you can see that C dot count, that will be equal to 1. That's it. Very easy. Okay, because 1 C is generated. Yes or no? 1 C is generated. So I can say C dot count is equal to 1. Very simple. What about this here? Here you can notice that 1 C is generated, but how many C are generated by this C? So tell me, how many C's are generated by this C? Now there is a confusion. When I am talking about C, I am talking about this capital C or this capital C. So just to differentiate that, let's use a subscript C1. Let's call it C1. Let's call it C2. Of course, both are capital C, but just to differentiate which C I am talking about, left C or right C. So I'm using this subscript. Okay. Now you tell me. So what will be C1 dot count? What will be C1 dot count? Tell me. C1 dot count, what that will be? That will be equal to 1 small c is generated. And how many C's are generated by C2? Yes or no? So very simple point, that C1 dot count will be equal to, what is C2 dot count plus 1? Very easy. Okay, yes or no? Means how many C's are generated by this C2 plus 1. So that will be the C1 dot count. Okay, very simple. Now similarly you can do for B comma A. So let me quickly write. So you can see that here, for this, with this production, what semantic action I will attach. So you can see that is basically that B dot count is equal to 1. Okay, here one small b we are generating. Okay, and what about this? So here you can see that, let's call it b1, let's call it b2. So you can see that b1 dot count, what will be b1 dot count? That will be equal to, what is b2 dot count? Plus small b plus 1. Yes or no? Plus 1, because one small b is generated here, and how many small b are generated by b2? So b1 dot count will be equal to b2 dot count plus 1. Okay, similarly you can write for these productions. Okay, so here you can see that what will be a dot count? A dot count will be equal to 1. What will be a1 dot count? You can see a1 dot count, that will be equal to a2 dot count plus 1. Okay, very simple. So I hope you understood so far. It is very intuitive. See, everything is very intuitive, because the question is saying that this is the grammar, and this grammar will generate this language a power m, b power n, c power p. But we want to generate this language. To generate this language, we want number of a equal to number of b equal to number of c. Okay, so we need to count the number of a, number of b, number of c. Yes or no? So because we need to count the number of a, number of b, number of c, so with these non-terminals we will associate count attribute. Very simple, very intuitive. Yes or no? This count attribute we will associate with these non-terminals. And now you can see that with these production rules we are attaching the meaning. Like, what is the meaning of these production rules? What is the meaning of this production rule? You can see the meaning of this production rule, that is basically that this b we are generating, and this b2 will also generate. Yes or no? So you can see that this b1 dot count, that will be equal to 1 plus b2 dot count. Yes or no? So you can see that semantic actions, semantic rules we are attaching with the production rules. Okay, now let's see what about this s. In this production, what we need to check? You can see in this production basically we need to check that number of a generated by a, number of b generated by b, number of c generated by c, they must be equal. Yes or no? So let me do one thing with this variable s, with this non-terminal s. Let me associate attribute equal. Okay, this non-terminal s, with this non-terminal s, I am associating this attribute equal. What this equal attribute will do, let me tell you. This equal attribute will be true. This s dot equal will be true if count of capital A, count of capital B, count of capital C, if they are equal. Okay, yes or no? If the count attribute of capital A, count attribute of capital B, count attribute of capital C, if they are equal, then this s dot equal will be 1. Otherwise this s dot equal will be 0. Or I can say, if the count attribute of ABC, if that is equal, then the s dot equal will be true, otherwise it will be false. Okay, and remember, if s dot equal, if this attribute s dot equal, if that is false, then we will reject the parse tree, we will reject the input string. So you can see we will accept the input string. When do we accept the input string? We accept the input string only when this s dot equal is true, and this s dot equal will be true only when the count attribute of ABC will be equal. Are you getting my point? So you can see that this variable ABC, all these variables, they have count attribute. Yes or no? This count attribute of A, it is counting the number of small a generated by capital A. The count attribute of capital B, that is counting number of small b generated by the capital B. And this count attribute of capital C, it is counting the number of small c generated by the capital C. Yes or no? So you can see that these variables, these non-terminals have count attribute. We just need to check that the count attribute is having the same value. So you can see that with this non-terminal s, we are associating this attribute equal. Okay, and let me tell you how this equal attribute will be calculated, how this equal attribute will be computed. So let me tell you what we can write like this, that if count of A, or I can say that if A dot count, okay, if A dot count, because count is the attribute of A. Okay, so you can see like A dot count. Yes or no? A dot count. So you can see that if A dot count, is equal to B dot count, and b dot count is equal to c dot count. Okay, remember, if we are writing like this, that if a dot count is equal to b dot count and b dot count is equal to c dot count, then true, else false. Okay, so let me tell you one thing. This is the rule. This is the rule with this production. Okay, are you getting my point? Very simple, very intuitive. There is nothing here, because remember one thing, that we want to generate this language a power n, b power n, c power n. So all the other strings we want to reject, all the other parse tree for all the other strings, those we want to reject. We want to accept the input string if and only if number of small a equal to number of small b equal to number of small c. Yes or no? So only these strings we want to accept. So what we are doing here, you can see that in these productions we are counting how many small a, small b, small c are generated. Yes or no? Like for example, this a dot count, b dot count, c dot count, this is what we are calculating, this is what we are computing. And you can see in this production rule, we are checking, that this a dot count equal to b dot count equal to c dot count or not. So you can see, if a dot count equal to b dot count equal to c dot count, then this s dot equal will be true, otherwise s dot equal will be false. What this s dot equal means, this is an attribute with this non-terminal s, and this attribute will be true when a dot count, b dot count, c dot count are equal. Okay, that is the reason I'm using this word equal for the attribute. Okay, s dot equal, this equal word I'm using for attribute to indicate that this equal attribute will be true when a dot count, b dot count, c dot count are equal. Otherwise, this s dot equal, this attribute will be false. Okay, and remember, if this s dot equal, if this attribute is false, then the input string you can reject. If this s dot equal is true, then the input string you can accept. So you can see that this language we have generated. I hope you understood. So this is the very interesting thing. I hope you found this very interesting. I hope you loved it, basically, because this example is showing you the power of SDT. This example is showing you the power of semantic analysis. You can see this grammar, sorry, this language can never be generated by any context-free grammar. But with context-free grammar, if you have semantic rules, with context-free grammar, with the non-terminals, if you associate attributes, and also with the productions, if you attach the semantic rules, then this complete object, this is called syntax directed translation. Okay, this complete object becomes very powerful, and it can handle context sensitive features of the programming language. Okay, I hope you understood. So you can see that parsers cannot handle context sensitive features of the programming languages, but the semantic analyzers can handle using SDT. I hope you understood this example. I hope you loved it. Okay, so you can see what we have seen. We have seen the intro to the SDT. I hope you loved the intro to the SDT, and now you understand the power of SDT, that this syntax directed translation, this SDT, it can help you in semantic analysis. Or I can say the semantic analyzer will use SDT or SDD for semantic analysis. Just like your syntax analyzer will use context-free grammar for syntax analysis, similarly the semantic analyzer will use SDT or SDD for semantic analysis. Okay, just like your lexical analyzer will use regular expression for lexical analysis. So like that. Okay, I hope you understood the point. So far we have seen the intro to SDT. This was just an intro, nothing else. This was just to motivate you to study this SDT, or I can say SDD. Okay, both are different. SDT, SDD, both are different. Okay, that difference will become very clear as we move on. So let's see this. The principle of syntax directed translation, the principle, or I can say the idea of syntax directed translation, it basically says that the meaning of an input sequence is related to its syntactic structure. Okay, that is the reason this name we are using, that syntax directed semantic analysis, syntax directed translation. Okay, so you can see syntax directed translation, SDT, It is a compiler technique, or I can say compiler tool, compiler mechanism, in which semantic actions are attached. Read this. Semantic actions are attached to the grammar productions of a programming language. Also, the non-terminals of the grammar, they are associated with attributes. Okay. Which attributes? Which attributes we will associate with the non-terminals, that will depend on which type of static semantic check we want to perform. Are you getting my point? There are different type of semantic checks that we can perform. For example, variables should be declared before use. Okay, for example, in the function call, the number of parameters and the type of parameters, they should match with the function declaration. So basically, there are different types of semantic checks that we can perform. So depending on what type of semantic check we want to perform, depending on which type of semantic analysis we want to perform, we can attach, we can associate attributes with the non-terminals, and according to that only, according to the check, according to the semantic check that we want to perform, we can attach the semantic rules with the grammar. Okay, overall the point is that what we are doing with the grammar, with the context-free grammar, we are associating attributes to the non-terminals, and also we are attaching the semantic rules to the productions. Okay, which semantic rules we will attach, which attributes we will associate with the non-terminals, that will depend on what type of semantic analysis you want to do, which type of static semantic check you want to perform. Okay, is that clear? So very simple. So you can read this here, that syntax directed translation SDT, this is a compiler tool in which semantic actions are attached to the grammar productions of the programming language. In SDT, the syntax means the grammar structure. It directly drives, okay, it drives the translation. Translation means the meaning related processing. Meaning related processing means semantic analysis basically. Okay, so you can see that in SDT, the syntax or the grammar structure directly drives the translation or meaning related processing, hence the name, this syntax directed translation. Okay, I hope you understood. Now let's see the difference between SDD and SDTS. Okay, so basically I told you that there are two different notations, there are two different tools, they are related to each other, but actually they are different. There is difference, but they are related to each other. Don't worry, we will see how they are related to each other, how they are different. Okay, so you can see, let's understand the difference between SDD, that means syntax directed definition, and SDTS, that means syntax directed translation scheme. Okay, this syntax directed translation scheme, it is also called SDT, syntax directed translation, but most of the time we call it syntax directed translation scheme, or you can call it translation scheme. Okay, so in short we call it SDTS, syntax directed translation scheme, and SDD means syntax directed definition. Sometimes we will also call this SDT only. Okay, both are fine, both are interchangeably used. So let's see the difference between SDD and SDT. Okay, so let's see this. Let's see this. There are two notations for attaching semantic rules. Remember, in both of them, syntax directed definition as well as translation schemes, these are two different concepts, two different notations. Okay, so one of them is specification friendly. For example, from the human point of view, if I want to define something, some static semantic check I want to perform, then from my point of view, from the human point of view, I can say that this syntax directed definition, this will be easier to write. Okay, more easily we can write it. But remember, from the implementation point of view, these translation schemes are better. Okay, so anyway, don't worry, this will become very clear. But right now, let's see this, that there are two notations for attaching the semantic rules. Okay, in both of them, syntax directed definition, also syntax directed translation scheme, in both of them, what we do with the context free grammar, we attach the semantic rules. Okay, is this clear? Also, with the non-terminals, we associate attributes. Okay, with the non-terminals, we associate attributes. So you can see what is the difference between them, that we will see. So let's see this. Syntax directed definition, this is high level specification. hiding many implementation details. Okay, so in this syntax directed definition, basically we are hiding the implementation details, like how it will be implemented. Okay, that we are hiding. It is just high level specification. Like on the high level, we are just specifying it. Okay, we are hiding the implementation details, like how it will be implemented, how it will be executed, how it will be evaluated. These details we are not mentioning. Okay, but in the translation scheme, means syntax directed translation scheme, or I can say SDT, or I can say SDTS. So in this SDT, what we do here, it is implementation oriented, means explicitly in the SDT, explicitly we mention what is the order of evaluation. Okay, is this clear? So you can see that indicate the order of evaluation of semantic rules in SDT. Okay, so remember these translation schemes, they explicitly, or I can say inside them, explicitly we indicate the order of evaluation of semantic rules, like in which order the semantic rules will be evaluated. That is explicitly stated, that is explicitly indicated in the SDT. So these are implementation oriented, implementation friendly. Okay, so you can read this, that between the two notations, the syntax directed definition, these are more readable, I told you. Okay, because these are high level specifications, so these are more readable and hence more useful for specification. Means from the human point of view, these are more useful, okay, to write the specification. So these are more useful. And you can see the translation schemes, they are more efficient for the implementation, for the evaluation, for the execution. So they are more useful for implementation. Okay, one more thing, SDT, these are basically, these can be viewed as implementation of SDD and are important from efficiency perspective. Basically, what will happen, let me tell you. Okay, I know you might not be understanding these things, but don't worry. By the end of this lecture, you will become expert in the translation schemes. Okay, syntax directed translation schemes. By the end of this lecture, you will become expert of this translation schemes. And in the next lecture, you will become expert of SDD. Okay, and slowly the difference of SDD, SDTS, that will become very clear. Okay, right now I am just telling you the definition, nothing else. If you did not understand, don't worry, because we will study this separately. We will study this separately. Then automatically you will understand the difference between them. Okay, yes or no? Is this clear? But right now, just let me tell you that you can see SDD. These are high level specifications hiding the implementation details. So from the human point of view, we can specify, we can write SDD, and when we need to evaluate, when we need to execute, when we need to implement, then we can convert these SDD to SDT. Okay, these SDD we can convert to SDT. So you can see SDT, these can be viewed as implementation of SDD and are important from efficiency perspective. Okay, so both are important, of course, both are important. So first we will study translation schemes, SDTS, or I can say SDT. In the next lecture, we will study SDD. But let's see one analogy. Okay, to understand what is the difference between SDD, SDT, just one analogy I want to share with you. Okay, if you have studied DBMS subject, in the DBMS subject we have relational algebra, SQL. These are the languages in the DBMS subject. This analogy you can understand if you have studied DBMS subject. If you did not study DBMS subject, then don't worry about this analogy, because this is not a concept, this is just an analogy. Okay, so let's understand the difference between SDD and SDT using one analogy. So you can see SDD, these are like SQL languages, means these are declarative. These are high level specifications. These are just declarative. They will tell you what to do. They will not specify how to do. It's like this. I tell you, make tea. I don't tell you how to make tea, like what will be the procedure. Okay. So remember SDD, this will tell you what to do. This will not tell you how to do. So when you are, let's assume that I want to check some static semantic property. Okay. Some static semantic check I want to perform, some semantic analysis I want to perform, some particular type of semantic analysis I want to perform. Now, To perform that semantic analysis, if I write SDD, syntax directed definition, if I write, then remember, in the syntax directed definition, I will just mention what to do. I will not mention how to do, how the semantic actions will be executed, in which order they will be executed. I will not mention it. I will just mention what I want. Okay, yes or no? What to do, I will mention. How to do, I will not mention. So you can see SDD. This is like SQL language, means these are declarative. And SDTS, these are like relational algebra language, means these are procedural. In SDTS, we explicitly mention how to do and what to do, both. Okay, means what to do as well as how to do. How to do means what will be the order of evaluation of semantic rules, in which order the semantic rules will be executed, in which order they will be evaluated. Okay, basically, in this SDTS, we mention the complete procedure, I can say. Step by step procedure is mentioned. Okay, so you can see that SDD does not specify evaluation order. In SDD, we just specify what we want, or I can say what to do. We don't specify how to do. So you can see SDD does not specify evaluation order, just like SQL. SDD just specifies what result you want, not how to compute it. Okay, and what this SDTS will do? SDTS will specify when the actions will execute, in which order they will execute. Okay, yes or no? So when the semantic actions, semantic rules will be executed. So you can see that execution order is explicitly specified in the SDTS. Okay, in SDTS, the position of semantic action, actually, the position of the semantic action in the production body, it will determine the order in which the action will be executed. Right now it will not be clear, right now you will not understand this, but by the end of this lecture, this paragraph, particularly this SDTS paragraph, will become very clear. Okay, that in this SDTS, the actions, the order of evaluation of semantic rules, the order of execution of semantic actions, that is explicitly specified. Okay, now let's move on. Now we need to study basically two concepts we need to study now: SDTS, syntax directed translation scheme, and all its gate PYQs. Also SDD, syntax directed definition, and all its gate PYQs. In this lecture, we will study SDTS and all its gate PYQs we are going to solve. Now we will study SDTS, means syntax directed translation scheme. You can also call it translation scheme in short. Okay, or also you can call it SDT. You can also call it syntax directed translation. Okay, so these are different names for it. So what is this SDTS? Let's try to understand. So far, whatever we have seen, just forget about that for a moment. Okay, because now we will study SDTS, syntax directed translation, or syntax directed translation scheme, or translation scheme, and just try to understand this. Okay, because this is very important in the GATE exam. From this SDTS, a lot of questions have come. All those GATE questions we will solve in this lecture. Okay, and let me tell you, this is the most easy topic. By the end of this lecture, you will think that this is the most easy topic. Okay, so right now, if you are having some confusion about SDT, SDD, okay, the difference, the similarity, so just forget about that. Okay, in this lecture, our focus will be to understand SDT. In the next lecture, we will understand SDD. Okay, so let's start now. Now let's understand what is SDT. The definition is very simple. Basically, SDT, or I can say the syntax directed translation scheme, this is basically context free grammar plus semantic rules. Semantic rules are embedded in the production bodies. Very simple. Okay, so the definition is very simple. Basically, in this syntax directed translation scheme, what we do, we have the context free grammar. In that context free grammar, with the grammar symbols, we associate attributes. That is one thing. Okay, with the grammar symbols, we associate attributes. And also, in the production bodies, we can embed semantic rules. Okay, so that's it. What you get, that is your SDTS, means syntax directed translation scheme. So let's see the definition. You can see the definition here. It is very easy definition. You can see a syntax directed translation scheme, SDTS. This is a context-free grammar with program fragments embedded within the production bodies. Production bodies, what it means? It means the right side of the production. Okay, so you can see a syntax directed translation scheme, SDT in short, is a context-free grammar with program fragments embedded within production bodies. Okay, these program fragments are called semantic actions or semantic rules, and they can appear at any position within the production bodies. Means on the right side of the production, they can appear these semantic actions, these program fragments, they can appear at any position. Okay, by convention, we place curly braces around these semantic actions. So you can see that this type of context free grammar with semantic actions embedded on the right side of the production rules, that is called your SDTS. Okay, you can see A going to XY. This is a production of the grammar. And now what we are doing on the right side of the production, we are embedding semantic actions. Okay, or I can say the program fragments we are embedding. These program fragments are called semantic actions, and you can see that these semantic actions, they can appear at any position on the right side of the production. Okay, multiple also are possible. It's not like only one semantic rule will be there, one semantic action will be there on the right side. On the right side, for example, you can have all these three semantic actions. Okay, or you can have only this, or you can have only this, like that. I hope you understood. So the definition is very simple, that context free grammar plus semantic actions on the right side of the productions. Okay, so that is your SDTS. Very easy. So let's see this. You can see a translation scheme, or I can say syntax directed translation scheme, or I can say SDT. This is a context free grammar in which attributes are associated with the grammar symbols. Okay, with the grammar symbols, like with the non terminals, we associate attributes, and semantic actions are inserted within the right side of the productions. Okay, so this type of situation, I hope you understood. And you can see one thing, how to evaluate, how to execute a translation scheme. If a translation scheme is given to you, then how to evaluate, how to execute? So let me tell you, it is very easy. The translation scheme, it actually describes the order and timing of the attribute computation, or I can say the translation scheme, it explicitly describes the order in which the semantic actions will be evaluated, the order in which the semantic actions will be computed. Okay, in this example, you can see, let's assume there is a semantic action A1 here, semantic action A2 here, semantic action A3 here. Okay, so you can see if these are the semantic actions, then you can easily notice that here it is very clear in which order these semantic actions will be evaluated, in which order these semantic actions will be computed. So you can easily see that before this X, this semantic action A1 will be executed. Okay, then you can see immediately after this X, before Y, okay, after X, before Y, this semantic action A2 will be computed. After Y, this semantic action A3 will be computed. Okay, is this clear? Very simple. So you can see that these translation schemes, they explicitly describe, they explicitly tell you the order in which the semantic actions will be performed, or I can say the order in which the attributes will be computed. So that is given explicitly in the translation scheme. Okay, very simple. Now let's see some examples here. These are the examples of syntax directed translation schemes. Okay, you can see this is a syntax directed translation scheme, because what you have basically context free grammar, and in the context free grammar, on the right side of the productions, we are embedding the semantic actions, or I can say the program fragments. For example, this is a program fragment, you can see, or I can say this is a semantic action, and this semantic action we are placing it between plus T and R. Yes or no? Basically, in the middle of this production, in the middle of this production body, we are placing this semantic action. Okay, I told you that in the syntax directed translation scheme, the semantic actions can appear on the right side of the productions anywhere. At any position, the semantic actions can appear. Okay, they can appear in the middle of the production also. or they can appear at the right end of the production. You can see, okay, here you can notice that this is another semantic action, or I can say this is another program fragment which we are putting at the right end of this production. Okay, yes or no? Very simple. So you can see that this is basically a translation scheme. Okay, another translation scheme we have here. In this translation scheme, there is one interesting thing, that all the semantic actions, these are placed at the right end of the productions. Yes or no? Basically in middle of the production, or to the left of the production, we don't have any semantic action. Okay, in this translation scheme, in this SDT, the semantic actions are placed at the right end of the productions. Okay, yes or no? Okay, notice one more thing, that it is not necessary that every production we have to put semantic action. It is not necessary. In this example, you can notice that with this production rule, we are not embedding, we are not attaching any semantic action. Similarly, with this production rule, we are not attaching any semantic action. Okay, with this production rule. Very simple. You can consider another example here. This is also translation scheme. Here also you have this context free grammar plus the semantic actions, the program fragments are embedded on the right side of the productions. Here also you can notice one thing, that all the semantic actions, these are placed at the right end of the productions. Yes or no? In the middle of the production or to the left of the production, we are not putting any semantic action. All the semantic actions, these are placed at the right end of the productions. And notice one thing, that with this production, we are not attaching any semantic action. Okay, is this clear? Very simple. So it is not necessary that we have to attach the semantic action with every production. It's not necessary. Okay, so you can see this is another SDT, or I can say translation scheme. This is another translation scheme. In this translation scheme, you can notice that this is a semantic action, and this semantic action we are putting to the left of this production rule. Yes or no? Okay, on the right side, of course. Okay, all the semantic actions, all these program fragments, they will be embedded on the right side of the production rules. Okay, but you can see on the right side also, like on the left side, we cannot, we will not embed the semantic actions. Okay, is this clear? The semantic actions will be embedded, the semantic actions will be attached on the right side of the production rules. But the point is that if you look at this production, then, or I can say this is the production body. To the left of this production body, we are putting this semantic action. Okay. Similarly, this semantic action is placed to the left of this production body. And you can see this semantic action we are placing here to the right of this production body. Okay. And you can see that, for example, these production rules, with them we are not attaching any semantic action. Okay, very simple. So I hope you understood. These are some examples of SDTS, syntax directed translation scheme. The definition is again very simple. Again, let me just revise it, that the syntax directed translation scheme, this is basically a context free grammar with program fragments embedded within the production bodies. Production bodies means to the right of the production rule, like on the right side of the production rule. Okay, but remember, the program fragments, these are called semantic actions, and they can appear at any position within a production body. Okay, this is the production body, and in this production body, these semantic actions, they can appear at any position. Okay, very simple. And these examples we have already seen. I hope you understood. Now let's see how to execute, how to evaluate a syntax directed translation scheme. If a syntax directed translation scheme is given to you, how to execute it, how to evaluate it, how to compute it. Okay, so let's see this. So you can see evaluation of syntax directed translation scheme SDTS. And it is actually very simple, let me tell you, because the syntax directed translation scheme, it explicitly tells you the order in which the semantic actions have to be executed. Okay, so let me explain this point. You can see the position of the semantic action. Read this point. The position of the semantic action in the production body. In the production body, the position of the semantic action it will determine the order in which the action is executed. Okay. Overall, let me tell you, if a SDT means if a translation scheme is given to you, then what you need to do, how to evaluate, very simple. What we will do for the input, there will be input, and this translation scheme, this syntax directed translation scheme, it will convert that input to output. Okay. So for the given input, what we will do, very simple. Any SDT, whatever SDT you take, whatever syntax directed translation scheme you take, whatever translation scheme you take, so you can see that any SDT can be evaluated by first building the parse tree. First, you create the parse tree for the input. Remember, when you are creating the parse tree for the input, then while creating the parse tree, we also make nodes for the semantic actions. For the semantic actions, also we make node in the parse tree. In the parse tree, for the semantic action, also we make node. And then what we do? Then we perform the actions in a left to right depth first order. That is a pre-order traversal. So what you do? First you build the parse tree with nodes for semantic actions too. Okay, for the input string, you build the parse tree with the nodes with the nodes for semantic actions too. And then what you do? In this parse tree, you just perform left to right depth first order. Okay, go left to right depth first order. Very simple. Now you can see during this left to right depth first order, as soon as you reach a semantic action, immediately execute it. Okay. During this left to right depth first order, as soon as you reach a semantic action, immediately execute it. That is the reason I am saying that during a pre-order traversal. Because in the pre-order traversal, what we do? Basically, the root, first root, then left child, then right child. Yes or no? So similarly, the same thing I'm saying here. You can see during left to right depth first order, as soon as you reach a semantic action, immediately execute it. Okay, this is the concept. Now we are going to take a lot of examples. Don't worry, this topic is actually very easy. Once we are done with the examples, you will feel that this is the most easy topic in the compiler design. Okay, so let's see this example. Consider this example. A syntax directed translation scheme is given to you. You can notice this is a syntax directed translation scheme. In this, what we are doing here, in the context free grammar, on the production bodies, we are placing the program fragments which are called semantic actions. Yes or no? These semantic actions are embedded in the production bodies. Yes or no? So overall, this structure, overall, this is called syntax directed translation scheme. Remember, this structure is not called grammar, because now this is no longer a grammar. This is a syntax directed translation scheme, because this is basically grammar plus semantic actions embedded in the production bodies. Okay, is this clear? So you can see now this structure is now called syntax directed translation scheme, or I can say SDT. So you can see this is your SDT. What is the translation for a plus b plus c? So for this input a plus b plus c, what will be the translation? What will be the output? Okay, so let's find this. It is actually very easy. I told you what to do. You just create the parse tree, and then you perform left to right depth first order. Okay, yes or no? So let's first create the parse tree. Creating parse tree is actually very easy. And when you create the parse tree, then you make nodes for the semantic actions too. Don't only make the nodes for the variables, or I can say for the grammar symbols, you also make the nodes for the semantic actions too. Okay, so you can see our input is a plus b plus c. So this is the start symbol. E is the start symbol. Of course, we will start from the e. E is the start variable. Okay, so you can see our parse tree, the root node is basically e. Then you can see this e will go to tr, because there is only one production for e. There is only one e production, so e will go to tr. Okay, next you can see that t will go to id print id name. Okay, notice one thing, t will go to id, but I told you that we will make node for semantic actions too. Yes or no? So remember what you need to do. Please understand, you consider this semantic action as a terminal. This semantic action you consider as a terminal. It's like this. You consider this as t going to id print id name. Okay, is this clear? So t going to id print id name. Okay, print id dot name. Okay, is this clear? This is the semantic action. Very simple. Okay, now let's see this R. This R will go to what? You can see this R will go to, I need total 2 plus I need. Okay, total 2 plus I need. So this R will give me 1 plus this R will give me. So you can see this R will go to plus. Okay, R will go to plus. This plus is the grammar symbol. And this plus, you can see print plus. This we are printing. And this plus is basically your terminal symbol. Okay, so you can see R will go to plus T. Notice one thing. You assume that this is like R going to plus T, this. Total 4 things. R is basically going to total 4 things. Similarly, here, T was basically going to 2 things. Okay, so you can see R will basically go to 4 things. Here, what you will do? Here you will print plus. Okay, and here there is R. Okay, notice one thing. This is also R. This is just to differentiate between this R and this R. We are using R1 here. Okay, but actually this is also non-terminal R. Okay, now you can notice this non-terminal R. It will go to again plus T, basically again this, because remember we already got 1 plus. Okay, this plus we got here. We want another plus we want. Okay, this is a semantic action, remember. Here, this is not your grammar symbol, or I can say this is not your terminal symbol. Okay, this is just a semantic action. So don't say that, okay, I got 2 plus. No, you did not get 2 plus. Okay, in the input string we have 2 plus. So far we got only 1 plus. Okay, because of this. I hope you understood. So you can see this R will go to what? I can say this R will go to plus. This R will go to plus, then T, then here print plus. Okay, and then R. Now what we got? We got 2 plus we got. Okay, so that's it. We want 2 plus, we got 2 plus. So you can see this R can go to epsilon. Okay, next you can see this T. This T will go to, remember this T will go to ID followed by print ID name. Okay, yes or no? Similarly, this T will go to ID followed by print ID name. Okay, similarly, this T will go to ID. This T will go to ID and print ID name. Okay, is this clear? Very simple. I hope you understood. So now the parse tree is ready. Once the parse tree is ready, then what we need to do? We just need to perform left to right depth first order. Okay, so let's go left to right depth first order. Let's go. Okay, so you can see we will start from here. Just keep going. You can see, and as soon as you reach a semantic action, immediately execute it. Okay, this is what I told you, right? You can see during left to right depth first order, as soon as you reach a semantic action, immediately execute it. Okay, so you can see we are going like this. As soon as you arrive this semantic action, immediately execute it. So what we need to do here, we need to print ID name. Now let me tell you one more thing. Actually, this ID, this is just a token name, right? Okay, ID is a token name. And what is the lexical value? That is basically here A, here B, and here C. Okay, is this clear? So, or you can say like this, you can write in the bracket that, okay, this ID is A, this ID is B, this ID is C. Okay, is this point clear? Because this is the input string that we want, A plus B plus C. So you can see that this ID, this is just a token name, and this is the lexeme. Okay, means the actual value. Okay, so you can see this is the actual value associated with it. So you can see this ID is basically A, this ID is B, and this ID is C. Okay, now let's perform left to right depth first. Okay, so you can see that as soon as you reach a semantic action, immediately execute it. Okay, immediately execute it. So you can see what we need to do. We need to print ID name. Okay, which ID name we will print? Of course, we will print this ID name. Yes or no? Because this action is associated with this production. Okay, this action is associated with this production. So you can see here we need to print ID name. So this ID name means A we will print. Okay, so remember in the output what you will get A. Next you can see, of course, what we will do. We will go like this. Okay, or I can say that then after that, okay, here you can see, then you keep going. Okay, remember what we are doing? We are doing left to right depth first. Okay, as soon as you arrive at any semantic action, then what you do? Then you execute it. For example, yes, this is the semantic action. As soon as you reach a semantic action, immediately execute it. So here we need to print ID. Which ID we will print? This B we will print, because this action is associated with this production. Yes or no? With this production, this action is associated. So we need to print ID. Which ID we will print? This B we will print. Okay. Then again, you just carry on. Left to right depth first. Okay. Then again you can see, this is the action, semantic action. As soon as you reach a semantic action, immediately executed. So you need to print plus. Okay, then you can see, then you keep going like this. As soon as you reach a semantic action, here you can see this is the semantic action. We are reaching the semantic action. So here what you need to do? We need to print ID. This semantic action we need to execute. We need to print ID. Which ID we will print? C we will print, because this action is associated with this production. Okay, so you can see this C we will print. Next you can see, okay, we will go like this, then print plus. Okay, we will also print plus. And then you can see that we are going like this, then that's it. Okay, so I hope you understood. Okay, clear? So finally the output that will be A, B plus C plus. This will be the final output. This is your translation of A plus B plus C. I hope you understood. Very easy, right? You can see the explanation here. This is the input and the output is A, B plus C plus. Actually, this SDT, this syntax directed translation scheme, this basically what it is doing, it is converting infix expression to postfix expression. Infix to postfix. These concepts like infix, postfix, all these concepts you can study in the data structure subject. Okay, these have been covered in the data structure. Okay, so basically this is the parse tree that you will get. Okay, I told you first you create the parse tree, and in the parse tree, remember, you also create nodes for the semantic actions. Okay, and then what we need to do? Then very simple, left to right depth first order. Okay, depth first traversal, left to right, that's it. Executing the semantic actions in that order. Okay, just keep going, left to right depth first order, executing the semantic actions in that order. Means as soon as you reach a semantic action, okay, immediately execute it. Okay, very simple. Let's consider this example. A syntax directed translation scheme is given to you, means SDT is given to you. What is the translation for 3 into 5 plus 4? Okay, remember, this is a syntax directed translation scheme, because what is the definition of SDTS, or I can say SDT? What is the definition? Definition is very simple, that is SDTS, this translation scheme, syntax directed translation scheme, this is a context free grammar with program fragments embedded in the production bodies. These program fragments are called semantic actions. And remember, in the production bodies, these program fragments can be placed anywhere. These program fragments, or I can say semantic actions, these can appear anywhere at any position in the production bodies. Okay, so now let's see what is the translation for 3 into 5 plus 4. The concept you already know. How to evaluate a translation scheme, how to execute a translation scheme? Very simple. For the input, you create parse tree. When you are creating the parse tree, then remember, we also make nodes for the semantic actions. Okay, it's like this. This is what you consider, that E is going to, this is one, then this, then this, then this. Okay, it's like this. I hope you are getting my point. Okay, similarly, T is going to print star, then T1, then star, then F, like that. Okay, so you make the parse tree including the semantic actions. Okay, including the semantic actions, you make the parse tree for the input string, and then in that parse tree, you perform left to right, depth first, traversal, depth first order. Okay, very simple. So let's see this here. What is the translation of 3 into 5 into 4? So first you create the parse tree. Okay, so let's create the parse tree now. We want star, we want one star, one plus, and remember this star must be before plus. Okay, this is what we want. So the start variable, that is L, this is the start variable. Of course we will start from the start variable. The root node of the parse tree, that will be the start variable. Okay, so the start variable is your root node. Then you can see L is simply just going to E, nothing else. Okay, L is going to E. Then you can see this E, this, we want one star, one plus, so you can see this E will go to what? Notice this E will go to E plus T. But notice one thing, that when you are making the parse tree, you make the parse tree including the semantic actions. So remember, it's like this, that E will go to print plus, then even, this even is same as E. Okay, and this T. So you can see this E will basically go to print plus. Here you print plus, then E, then plus, and then T. Please understand, this print plus, this is a semantic action, and this plus, this is your terminal in the input string. Okay, very simple. So you can see we got 1 plus. Don't say that we got 2 plus, because this is a semantic action and this is the terminal, this is the terminal symbol in the input string. Very simple. Okay, so you can see, very simple, we got 1 plus. Now we want star to the left of plus. Yes or no? To the left of plus we want star. So remember, from this E, somehow we need to create a star. Okay, so what we will do? This E will go to T. Okay, this E, this will go to T. E will go to T. Next, you can see that this T need to create a star. Okay, so what this T will do? This T will go where? Notice, this T will go to print star T star F. Okay, so this T will go to print star T star F. Okay, so you can see that we got star also, we got plus also. So that's it. This is what we wanted. Now what we can do? Now you can see that here this T can go to where? This T will go to F. Okay, you can see this T will go to F. And this F will go where? Notice, this T will go to F. Then this F will go where? You can see, notice here, that F will go to digit followed by print digit dot lexical value. Okay, yes or no? Means this digit, for this digit, this is the token. We need to print the lexical value of this digit. Okay, is this clear? So you can see that this F will go to digit, this F will go to digit, here print digit dot lexical value. Okay, very simple. Similarly, this F, what this F will do, what, where this F will go? This will also go to digit, this will also go to digit followed by print digit. Okay, and similarly this T will go to F, and again this F will go to digit print digit. Okay, so I hope you understood. This is the parse tree that we got. Okay, you can see we got our parse tree. Now once we got our parse tree, then what we need to do? Very simple, we need to perform left to right, depth first, traversal. Okay, first of all, let me tell you that, like this digit, this is the token. What is the lexical value? That is basically 3. This digit is basically 3. This digit is basically 5. Okay, you can see this digit, this is basically 5. And this digit, this is basically 4. Okay, so now let's see what we will do. We will perform left to right depth first traversal. Okay, so keep going. As soon as you reach a semantic action, immediately execute it. So what we will do, we will print plus. So in the output, what we will get, we will get plus. Okay, as soon as you reach a semantic action, immediately execute it. Keep going, depth first. As soon as you reach a semantic action, immediately execute it. So we will print star. Okay, keep going, depth first, left to right, depth first. Okay, keep going, digit. Okay, keep going. As soon as you arrive at, as soon as you reach a semantic action, immediately execute it. Okay, so you can see print digit lexical value. Which digit lexical value we need to print? You can see this action is associated with this production. So this digit, this lexical value 3 we need to print. Okay, then you just keep going. Okay, keep going. Okay, keep going like this. As soon as you arrive at a semantic action, immediately execute it. So here we need to print digit. Which digit we will print? You can see this semantic action, this is associated with this production. Yes or no? This production. Okay, so you can see that here this 5 we will print. Okay, then you just keep going. Left to right, depth first order. Okay, then you can see that as soon as you arrive at semantic action, immediately execute it. Here we need to print digit. Which digit we will print? So that is basically, you can see this semantic action is associated with this production. So we will print 4. Okay, and then finally you can see, just keep going. Okay, that's it. So you can see the output will be plus star 354. This will be your output. I hope you understood. Okay, you can see this is the tree, this is the parse tree with semantic actions. Okay, yes or no? You can see parse tree with actions embedded. So you just need to perform left to right depth first order, and you can get the output, the translation, that will be plus star 354 plus star 354. This is what we got. Okay, very simple. I hope you understood. So basically we have seen how to evaluate a syntax directed translation scheme. We have seen the definition of syntax directed translation scheme. We have seen how to evaluate it. And the evaluation of syntax directed translation scheme, this is very easy. What we need to do, we just treat the semantic actions like they are terminal symbols of the grammar. Okay, yes or no? Means when you create the parse tree, then including the semantic actions, we create the parse tree. And then we perform left to right depth first order. Okay, very simple. So you can read this, that an action may be placed at any position within the body of a production. This we already know. In the syntax directed translation scheme, what is this? This is a context free grammar with semantic actions which are placed at any position within the body of a production. Okay, now you can see it is performed immediately after all the symbols to the left have been processed. Means I told you that syntax directed translation scheme SDT, it explicitly tells you when the semantic action will be executed. It explicitly tells you the order in which semantic actions will be executed and when a particular semantic action will be executed. For example, let's assume that you have this production. You can see B going to XY, but between X and Y, we are putting this semantic action. So remember, when this semantic action will be executed, this semantic action will be executed after X and before Y. Okay, is this clear? If X is a terminal, then after recognizing X, this action will be performed. This action will be executed before recognizing Y. Okay, is this clear? So you can read this, that the semantic action is performed, the semantic action is executed immediately after all the symbols to its left have been processed. Thus, if you have a production like this, where this action A, this is the semantic action, then remember this action A will be done after we have recognized X, if X is a terminal, or all the terminals derived from X we have recognized. Okay, basically the point is that after this X, this semantic action A will be performed. Okay, is this clear? Very simple. So this algorithm is there for the evaluation of SDT. We have already seen this. Okay, so you can see that any SDT can be implemented. Here, this implemented, this simply means evaluation, means execution. Okay, here they are using the word implemented, but actually in the context of SDT, this implemented, this word basically means execution, or I can say evaluation, or I can say translation. So you can see any SDT can be executed as follows. What we do? First, we ignore the action and then we make the parse tree. And then what we do? I told you that in the parse tree, you must make nodes for the semantic actions also. So actually in this algorithm, what they are doing, notice, first they are ignoring the action, then they are making the parse tree. Then remember in the step 2, they are adding the actions in the parse tree. So we have done this together. Step 1, step 2, we have done together in our examples. 2 examples we have seen. In those examples, you can see step 1, step 2. These 2 we have done together, not separately. Okay, we are creating the parse tree, including the semantic actions. Okay, overall the point is that in this step 1, step 2, overall the point is that including the semantic actions, you create the parse tree, and then what you do? You perform a pre-order traversal, or I can say you perform left to right depth first order traversal. Okay, as soon as you reach a node with semantic action, immediately execute it, immediately perform that action. Okay, so you can see here, as soon as a node labeled with action is visited, as soon as you reach a semantic action, immediately perform that action. Okay, very simple. I hope you understood. Let's see one more important definition in SDT, in syntax directed translation scheme. One more important definition, let's see, that is, what is postfix SDT? Means postfix translation scheme, or it is called postfix SDT. We will see the importance of postfix SDT, but let's see the definition first. So you can see the name itself is telling you postfix SDT means those SDT, those translation schemes where all the semantic actions are placed at the right end of production bodies. Means in middle of the production body, we don't put any action. To the left of the production body, we don't put any semantic action. Means all the semantic actions are placed at the right end of the production bodies. Then this type of SDT, this type of translation schemes are called postfix SDT. Okay, and these are important. I will explain why these are important, but I hope you understood the definition. So which of the following are postfix SDT? Let's check. Here some SDT, some translation schemes are given to you. Which of them are postfix SDT? So you can see this is not a postfix SDT. Okay, this is SDT, but this is not postfix SDT. Okay, so you can see this is SDT. This is SDT, but this is not postfix SDT. Postfix SDT, this is not postfix SDT. Okay, very simple. So because here you can easily see that this semantic action is not on the right end of the production body. This is actually in the middle of the production body. Yes or no? You can see in the middle of the production body, this semantic action is placed. Okay, so remember, this is not a postfix SDT. What about this? Is this postfix SDT? Yes, this is a postfix SDT, because here you can see that all these semantic actions, these are basically placed at the right end of the production bodies. Okay, here also you can notice that this is also postfix SDT. Okay, because all the semantic actions are placed at the right end of the production bodies. Okay. And what about this SDT? Is this postfix SDT? The answer is no, because you can see that this semantic action is not placed at the right end of the production body. Okay. So this is not a postfix SDT. Okay. I hope you understood the definition of postfix SDT. Postfix SDT means this is a syntax directed translation scheme, means this is a SDT with all the semantic actions placed at the right end of the production bodies. Okay, very simple. Now, why these postfix SDT are special? Why are we learning the definition of postfix SDT like this special category of SDT? Why are we learning? So, why they are special? Let's see. Before we see why these postfix SDT are special, let's quickly revise the basic concepts of bottom-up parsing. Okay, so let me quickly revise bottom-up parsing, the basic concepts. Okay, let's quickly see the bottom-up parsing recap. In the bottom-up parsing, the name itself is telling you, as implied by its name. In the bottom-up parsing, what we do? We start from the input string and we go toward the start variable. Yes or no? So you can see a bottom-up parser will construct a parse tree by starting from the input string. For the input string, the bottom-up parser will construct parse tree by beginning at the leaves, means by beginning at the string, by beginning at the bottom and working towards the root, means working towards the start variable, or I can say working towards the top. Okay, so this is basically the definition of bottom-up parsing. Now, in the bottom-up parsing, what we do? Basically, we are reducing the input string to the start variable, means we are basically applying the productions in the reverse order. So you can see in the bottom parsing, we apply the productions in the reverse order. We apply the productions to convert the input string to the start variable, or I can say to reduce the input string to the start variable. Remember, the bottom parser will scan the input string from left to right one symbol at a time. Whether you have top down parser or bottom parser, the input string we will scan from left to right one symbol at a time. And you can see the bottom up parser will construct rightmost derivation in the reverse order. Okay, so these are some basic points related to bottom up parsing. The bottom up parser basically what it does, it creates it constructs a rightmost derivation in the reverse order. Okay, so you can read this here. Bottom up parsing, if anyone asks you what is bottom up parsing, then remember this is basically same as construction of rightmost derivation in the reverse order. Okay, so what the bottom parser will do, it will build rightmost derivation in the reverse order. Okay, so you can read this, that this bottom parsing, this is a parsing technique where the string is recognized by constructing rightmost derivation in the reverse order, means we will start from the input string and we will work towards the root. Okay, very simple. Now you can see this statement that bottom up parser basically it will do everything what rightmost derivation does, but in the reverse order. Okay, remember, given a grammar and an input string, a grammar is given to you, input string is given to you, then remember the bottom up parser what it does, it constructs rightmost derivation in the reverse order. So remember, the bottom up parser will do everything that the rightmost derivation does, but in the reverse order. Okay, so you can read this: bottom up parser recognizes W by doing everything that rightmost derivation of W does, but in the reverse order. Okay, so you can see if this is your rightmost derivation, then whatever you are doing in this rightmost derivation, do it in the reverse order. That is your bottom up parser. Okay, very simple. So the bottom up parser will do what this rightmost derivation is doing, but in the reverse order, means every individual production will be applied in the reverse order, because this rightmost derivation, this is applying the productions in this order. So what this bottom up parser will do, bottom up parser will apply every individual production in the reverse order. Also, the order of productions, the sequence of productions, that also will reverse. Okay, and remember one thing, when you apply a production in the reverse order, that is called reduction. Okay, so you can see in this forward direction, this is derivation. In the forward direction, this is derivation, but in the reverse direction, this is reduction. When you apply a production in the reverse direction, that is called reduction. Okay, so in this direction, this is basically derivation. In this direction, this is basically a sequence of reductions. Okay, every step is a reduction. In the reverse order, every step is a reduction. Okay, very simple. So you can see this, that productions that rightmost derivation applies, bottom up parser will apply the same productions but in the reverse order. Also, for any individual production, at any step, for any individual production, if rightmost derivation is applying, let's assume this production a going to beta, means replacing a with beta, then what the bottom up parser will do? It will do the same thing in the reverse order, means it will replace beta with a. Okay, and remember, applying a production in the reverse order is called reduction. When you apply a production in the reverse order, that is called reduction. So if anyone asks you, given a grammar and a input string w, two things are given to you, grammar and input string w. If anyone asks you how many reductions will be performed by bottom up parser, then that is same as the length of rightmost derivation. Yes or no? Because I told you that bottom up parser will recognize w by doing everything that rightmost derivation of w does, but in the reverse order. So you can see that if this is your rightmost derivation, then you just reverse it. You just look at this in the reverse order. That is what the bottom parser does. And you can see that in the reverse order, if you apply a production, applying a production in the reverse order, that is called reduce or reduction. So you can see, if I ask you, given a grammar and an input string w, how many reductions are done, how many reductions are performed by bottom up parser, then that is same as length of rightmost derivation for w. And what is the order of reductions? That is same as reverse of order of productions applied. Yes or no? The order of reductions, that will be same as the reverse order of productions applied by rightmost derivation for w. The rightmost derivation is applying the productions in this order. Okay, so the order of reductions, that will be reverse of this order. Yes or no? Very simple. I hope you understood. So you can see this here. A top-down parser, what it does, it constructs leftmost derivation. It will start from the start variable. Yes or no? The top-down parser will start from the start variable and it will construct leftmost derivation. The bottom-up parser, it will start from the input string and it will create rightmost derivation in the reverse order, and it will reduce the input string to the start variable. So basically the bottom-up parser, it will start from the input string and at the end it will go to the start variable. The top-down parser, it will start from the start variable and it will go to the input string. Okay. You can see this. What is a reduction? Reduction is basically a reverse of a step in the derivation. Okay. In the derivation, the reverse of a step, that is called reduction. This is reduction, this is reduction, like that. Okay. Very simple. Now let me tell you one last point about bottom-up parser and top-down parser. So you can see, we have already seen that bottom-up parsing, this is basically same as construction of rightmost derivation in the reverse order. Okay. Now let me tell you two more important points. That is, bottom-up parser, it performs post-order traversal of the parse tree, and top-down parser, it performs pre-order traversal of the parse tree. Means, for a given grammar and input string, two things are given to you, grammar and input string, you create the parse tree. Okay, you generate the parse tree. Now once you generate the parse tree, then if you want to see how the top-down parser will generate this parse tree, then what you do, then you perform the pre-order traversal of the parse tree. And if you want to see how the bottom-up parser will build this parse tree, then what you do, then you perform post-order traversal of the parse tree. Why? What is the reason? What is the reason bottom-up parser will perform post-order traversal of the parse tree and top-down parser performs pre-order traversal of the parse tree? What is the reason? The reason is very simple, very intuitive. Notice, the top-down parser, it will start from the start variable. So pre-order traversal starts from the root, yes or no? So you can see that top-down parser, it will start from the start variable, means it will start from the root. So you already know that pre-order traversal, this also starts from the root, means the pre-order traversal, it will first print the root, yes or no? It will first print the root. Okay, similarly you can see the bottom-up parser for a given grammar and input string, you first create the parse tree. Then let's assume that you want to see how the bottom-up parser will generate this parse tree. You have created the parse tree, but now you want to see that how the bottom-up parser would generate this parse tree. From the bottom-up parser point of view, how this parse tree will be generated. Then what you do? You just perform the post-order traversal of the parse tree. Why? What is the reason? Because you already know that the bottom-up parser, it will start from the input string and at the end it will go to the root. Yes or no? At the end it will go to the root. Similarly, in the post order traversal, at the end we print the root. Yes or no? In the post order traversal, at the end we print the root. Similarly, the bottom up parser, it will go to the root at the end, and the top down parser, it will start from the root, and the pre order traversal, it will print the root at the beginning. So I hope you understood this. This is a very intuitive concept. Okay, that's it. So this is the summary, or I can say this is the recap of basic concepts related to bottom up parser. We will use some of these concepts. That is the reason this recap we have seen. Okay, whatever we have seen, that is written here. Okay, now I was discussing why postfix SDT are special. Already we have seen the definition of postfix SDT. What are these? These are those SDT, those translation schemes where the semantic actions are placed at the right end of the production bodies. Okay, so those are called postfix SDT. Now, why they are special? Let's see now. With example, it will become more clear, but let's see why postfix SDTs are special. Now, let's see why postfix SDTs are special. In the postfix SDT, the semantic actions can be executed along with the reduction of the body to the head of that production. Okay, what this statement is saying, let me tell you. Basically, when you are performing the reduction, then along with that reduction, or I can say immediately after that reduction, or I can say along with that reduction, you execute the semantic actions. Okay, so this is how you can evaluate postfix SDT. Now you might be thinking that we already know how to evaluate any type of SDT. Yes or no? Any type of syntax directed translation scheme, any type of SDT, if I give you how to execute, how to evaluate, that you already know. Okay, the general method you already know. What we will do? We will create the parse tree, including the semantic actions, and then we will perform the left to right depth first order. Yes or no? That is the general method for all the SDT. So that will also be applicable on postfix SDT. Remember, that method is also applicable on postfix SDT. But there is another method for postfix SDT, and this method is also very useful. In some questions, we will use this method. Okay, so you can see that why postfix SDTs are special, because if you have a postfix SDT and if you want to evaluate this, if you want to execute this, then what you need to do? One method is the general method that we have already seen, but there is another method, and this is more important method from postfix SDT point of view. And this method is basically that when you perform the reduction, then along with the reduction, you execute the semantic actions. Okay, so you can see in postfix SDT, the semantic actions are executed along with the reduction. And what is the reduction? Reduction means you are reducing the body to the head. Okay, I told you that when you apply a production in the reverse order, that is called reduction. So reduction means that the body you are replacing with the head. Okay, so very simple. So you can see that when you are performing the reduction of a production, then along with the reduction you can execute the semantic actions. Okay, so let's read this. A bottom up parser carries out the semantic actions specified within the braces. Of course, the semantic actions, these we specify within the braces that you already know. Okay, so if you have a postfix SDT, remember, for a postfix SDT, a bottom-up parser, what it can do, it can carry out the semantic actions. It can execute the semantic actions immediately after reducing the corresponding production rule. Okay, very simple. In short, I can say, in simple words, I can simply say that if you have a postfix SDT and you want to execute it, if you want to evaluate it, okay, then to evaluate the postfix SDT, what you can do, very simple. When you are performing the reduction, then along with that reduction, okay, together with that reduction, you execute the semantic action corresponding to that production. Okay, is that clear? Very simple. I hope you understood. But with example, it will become much more clear. But first, let me make some diagrams to explain this point. Okay, so you can see that what I'm saying. I'm saying that if you have a postfix SDT, then semantic actions can be executed along with the reduction. Okay, so let me make two diagrams to understand. First, let me make from rightmost derivation point of view. Okay, from rightmost derivation point of view. Let me explain this point from rightmost derivation point of view. So let's assume that we have this production. Let's assume we have A going to gamma, and there is a semantic action here. That semantic action is A1. Okay. Notice one thing, that the semantic action is placed at the right end of the production body. Okay, because we are discussing postfix SDT. Okay, in the postfix SDT, this is a SDT where all the semantic actions are placed at the right end of the production body. Okay, so let's assume that this is what we have in our SDT. Okay, I can say this is an object, or I can say this is a production in our SDT. This is an object in our SD postfix SDT. Okay, in our postfix SDT. Okay, now let's assume the input can be anything. Okay, let's assume there is some input W, and let's assume that you are creating the rightmost derivation for W. Okay, so you are creating the rightmost derivation for W. At the end, this is W. Okay, and when you are creating this rightmost derivation for W, let's assume that you are in this situation that at some point you have alpha A beta, and this is going to alpha gamma beta. Okay, basically what you are doing, this A is basically going to gamma. This A you are replacing with gamma. Okay, very simple. Now I told you that this is your rightmost derivation. Okay, you can see this is your rightmost derivation. This is the rightmost derivation. And I told you that the bottom-up parser, what it will do? It will do everything that this rightmost derivation is doing, but in the reverse order. Okay, the bottom-up parser, what it does? The bottom-up parser, it does what this rightmost derivation is doing, but in the reverse order. So you can see this rightmost derivation, what it is doing, it is applying this production A going to gamma. You can see what the bottom-up parser will do. It will replace this gamma with A. Yes or no? And I told you that when you apply a production in the reverse order, that is called reduction. Here basically you are reducing. When you apply a production in the reverse order, that is called reduction. Okay. Or I can say that this is your derivation. This is the rightmost derivation. And in the reverse order, you can see that reverse of any step, that is called reduction. See, this is one step. The reverse of this step, that is called reduction. Or I can say when you apply a production in the reverse order, that is called reduction. Now remember, if you have postfix SDT, then how to evaluate this postfix SDT? This is very simple. You can execute the semantic actions along with the reduction. Means along with this reduction, you can see this we are reducing gamma to A. Along with this reduction, we can execute this semantic action corresponding to this reduction, corresponding to this production. So remember, along with this reduction, together with this reduction, what we do? This reduction and execute the semantic action A1. Okay, and execute this action A1. Okay, is this clear? Very simple. I hope you understood this. So remember, along with the reduction, you execute the semantic action corresponding to that production which you are reducing. Okay, very simple. I hope you understood. Now let's see the same diagram from parser point of view, or I can say parse tree point of view. Okay, so let's see from parse tree point of view. Just to understand. Okay, let me make the diagram. From the parse tree point of view, let's understand this point. Okay, this above point. So again, let's assume that you have this production A going to gamma, and this semantic action is associated. You can see that this semantic action we have placed at the right end of the production body because we are discussing postfix SDT. Okay, so very simple. This is the semantic action. Now, for the input, there was input W. Okay, there was input W. Of course, for the input W, what you do? You create the parse tree. Now, you will create the parse tree. This is your input W. Okay, this is the input W. And you are creating the parse tree, right? Because bottom up parser, it will start from the bottom, from the input string. Okay, so you can see that you are creating the parse tree. Now, when you are creating the parse tree, let's assume you have already created the parse tree. Okay, because I told you that if you have a grammar and input, then first you create the parse tree. Then, if you want to see how the bottom up parser would generate this parse tree, how the bottom up parser would generate this parse tree, then what you can do? You can do the post order traversal, post order. Yes, you can do the post order traversal of this parse tree. Okay, that point we have already seen. Okay, but here what I'm discussing the evaluation of postfix SDT. Okay, evaluation of postfix SDT we are discussing. So here, this point I'm discussing that in the postfix SDT, the semantic action you can carry out along with the reduction. Okay, so let's assume that you have made the parse tree. Okay, after making the parse tree, I told you that once you make the parse tree, then what to do? Depth first, left to right. Okay, you perform depth first, left to right. Okay, and let's assume that this in this parse tree, let's assume we have A going to gamma, A going to gamma. Okay, in this parse tree, of course, there is big. Okay, this parse tree is there. Okay, in this parse tree, we have A going to gamma. Now you can see what we will do. We will perform left to right depth first. Yes or no? So let's assume you are performing left to right depth first. Okay, remember one thing I am saying that along with reduction, you perform the semantic action. Okay, so you are performing left to right depth first. You are performing left to right depth first. What this means? This means left to right depth first. You are performing left to right depth first. Okay, so let's perform this left to right depth first. And here, notice that when you reduce it, what is the definition of reduction? That is when you apply a production in the reverse order. Okay, now you can see that when you reduce it, means this gamma we are reducing to A. This is reduction. Okay, yes or no? This is your reduction. We are reducing gamma to A. So when you reduce it, now along with this reduction, what you do? You execute this semantic action corresponding to the production that you are reducing. Okay, so here basically this is called reduction. This is called reduction. And what you do? You execute action A1. Okay, I hope you understood this point. Okay, so basically very simple point. So this is the importance of postfix SDT. So remember, for the postfix SDT, we have two evaluation methods. Okay, again I'm telling you that when postfix SDT is given to you, then how to evaluate. One method is the general method, which is applicable, which is working for all the type of SDT, whatever SDT you take. But remember, for the postfix SDT, means when the semantic actions are placed at the right hand of the production bodies. So if you have postfix SDT, then how to evaluate? Then we have another method. And because this special method is for postfix SDT only, so for postfix SDT, most of the time we will apply this method. And if you have SDT which is not postfix SDT, then we will apply our general method. Okay, that we have already seen previously. So for postfix SDT, we are going to apply this method. Basically, overall, what we are going to do, when your postfix SDT input is given to you, we will first create the parse tree. Once we create the parse tree, then we will perform left to right, depth first. We will perform, and along with the reduction, whenever some reduction is happening, along with the reduction, we will execute the semantic action corresponding to the production that we are reducing. Okay, is this clear? Very simple. I hope you understood. Now, now we are going to solve a lot of GATE exam questions. Basically, all the GATE questions based on SDT, syntax directed translation scheme. Based on that, all the GATE PYQs we are going to solve now. Okay, let's solve GATE CS 1995 question. Question is saying that a shift reduce parser carries out the actions specified within braces immediately after reducing the corresponding rule of the grammar. Actually, notice one thing. Look at this SDT. Look at this syntax directed translation scheme. Look at this. This is postfix SDT. Because this is postfix SDT, that is the reason we can use this method to evaluate this postfix SDT. I told you one thing, that because this is postfix SDT, notice one thing, this is a postfix SDT. Why this is postfix SDT? Because the definition of postfix SDT we have already seen in this lecture. I told you the definition, very simple. Postfix SDT is a SDT in which the semantic actions are placed at the right end of the production bodies. So you can see all the semantic actions, these are placed at the right end of the production bodies. So this is a postfix SDT. And how to evaluate this postfix SDT? How to evaluate? To evaluate this postfix SDT, what you can do? You, of course, you make the parse tree, and then remember, along with the reduction, means immediately after you reduce a production, you you execute the semantic action corresponding to that reduced production. Okay, this is how we evaluate. Okay, so you can see postfix SDT, how to evaluate. Very simple. First you make the parse tree. Parse tree, when you make the parse tree, then without semantic actions, because remember, we are not using the general method. Of course, you can use the general method also. I told you one general method which will work for all the SDT, whether you have postfix SDT or you have SDT which is not postfix. So for all the SDT, there is a general method of evaluation that will work. But you can see, because this is a postfix SDT, so there is a special method, and that is that you make the parse tree without semantic actions. In the parse tree, you don't add semantic actions. So parse tree without semantic actions. And then what to do? Then the second step, that is left to right, depth first. Okay. Then what is the step number 3? Step number 3 is that along with reduction, along with reduction, along with reduction, execute corresponding semantic rule. Okay, execute corresponding semantic action. Okay, so this method, of course, we can use to evaluate postfix SDT. And in this question, we have postfix SDT. Actually, let me tell you that this question we are going to solve using three methods. Just for sake of learning, this question we will solve using three methods. You can select your favorite method and that you can use. Okay, three methods I am going to use to solve this question. Okay, so let's see the method number one, that is our general method, which will work for all the SDT, for all the syntax directed translation schemes. What is the general method that you already know? Let me recap. So you can see method number one, that is the general method for all the SDTs. So how to evaluate a syntax directed translation scheme? Very simple. What we will do? We will first build the parse tree with the semantic actions. Okay, means you build the parse tree with nodes for semantic actions too. So including the semantic actions, you build a parse tree. Then what you do? Then you perform left to right depth first order. Okay, this is what you perform. And when you are performing left to right depth first order, then as soon as you reach a semantic action, immediately execute it. Okay, yes or no? So this method number one, which is the general method for all the SDT, let's apply this method to solve this question. You can see the question is saying that what is the translation for this input, and this is the translation scheme given to you. So what is the translation for this input? Let's see. We will first create the parse tree including the semantic actions. Okay, so you can see, let's create the parse tree. The root of the parse tree, that is the start variable s. So this s, remember, notice one thing, because this is the method number one, the general method. General method for all SDTs. Okay, so here in this method, what we will do? We will generate the parse tree including the semantic actions. So you can see that this s, basically this s will go to xxw print1. It's like this. Okay, that this s will go to x x, this s will go to x x w, capital W, and here print1. Okay, very simple. Next, you can see these xx, these are basically terminals. Okay, so we got xx. What we want? We want another double x, y double z. So this w, of course, there is only one production for w. So this w will go to, remember, this w will go to s z print3. This w will go to s z print3. Okay, print3. Now let's see where this s will go to. You can see this s, because we want double x, right? Okay, so this s will again go to xxw print1. Okay, x w, capital W, print1. Okay, print1. Next, you can see what we got so far. What we got? We got double x, 4x we got, then z we got. We need y. Okay, you can see how many z we want. We want total 2z. So w was going to sz. Okay, so again we want another z, right? We so far we got only one z, we want another z. So this w, anyway, actually this w has only one production. So this w will go to sz print3. Okay, this w will go to sz print3. Okay, now this s will go to y. Okay, remember, this s will go to y print2. This s will go to y print2. Okay, I hope you understood this. So let's look at this parse tree. Did we complete it? Yes. Yes, it is completed. Okay, we have completed the parse tree. You can notice what is the yield of the parse tree? Means what is the string generated by this parse tree? Okay, for that, what you can do? You can just go left to right depth first. So you can see that it is basically double x, then y, then z, then z. Okay, so you can see double x, y, z, z. Is this clear? Now what we will do, so once we have this parse tree, basically once we have this parse tree with semantic actions, you can see with nodes for semantic actions. So remember, with semantic actions we have this parse tree. So what we need to do now just do the left to right depth first, yes or no, left to right depth first traversal we need to do. Okay, and as soon as you arrive at a semantic action, immediately execute it. Okay, very simple. So let's see, you can see we are starting our left to right depth first traversal, and as soon as I will arrive at a semantic action, as soon as I will arrive at a semantic action, I will execute it. So you can see we are performing our left to right depth first. Okay, yes, as soon as I will arrive at a semantic action, immediately I will execute it. So you can see what will be the output. In the output, I need to print 2. This action, this semantic action I need to execute, and this semantic action is telling me to print 2. So I will print 2. Very simple. Okay. Now you can see that. Just continue going left to right depth first. Okay. As soon as you arrive, as soon as you reach a semantic action, immediately execute it. Okay. So here, this semantic action is telling me to print 3. I will print 3. Okay, keep going. So you can see that. Okay, just keep going like this. As soon as you reach a semantic action, then execute it. Print 1. I will print 1. Okay, then you can see, just keep going left to right depth first. As soon as you reach at a semantic action, immediately execute it. This semantic action is saying print 3, so I will print 3. Okay, so here print 1, I will print 1. Okay, that's it. Is this clear? So finally the output, what is that? That is 23131. This is the translation of this input. For this input, this is the translation. Okay, I hope you understood. Very simple, right? So this is your method number 1. Now the same question, this same GATE 1995 question, let's solve using another method. Method number 1 is clear. In this method number 1, here what we are doing? Here we are doing left to right depth first order traversal. Okay, very simple. Now let's solve the same question with method number 2. What is method number 2? This method number 2 is only for postfix SDTs. This is only for postfix SDTs, because remember, in our GATE 1995 question we have postfix SDT. So for this postfix SDT, we can apply this method. Okay, so this method number 2, this is only for postfix SDT. What is this method? This method is again very simple, that in postfix SDT, the semantic actions can be executed along with the reduction. Okay, when you are reducing, then along with that reduction, you execute the corresponding semantic actions. Okay, the corresponding semantic action with the production that you are reducing. So that semantic action you can execute. Okay, very simple. Now let's solve this question with the method number 2. Now in the method number 2 also, I will solve from right mode derivation point of view, also from parse tree point of view. Okay, see, I am just telling you all the multiple methods so that your understanding about the concept becomes more deeper, or I can say you feel more connected. You know all the concepts, you feel more connected. Okay, so that is the reason I am telling you multiple methods to solve the same question, but eventually we will choose our favorite. Okay, after some time I will tell you that we will choose our favorite, and that favorite method we will apply in all the future questions. Okay, but right now, for just for complete analysis, or I can just for understanding purpose, I am telling you that the same question you can solve by multiple methods. All these methods are basically, in one way or another, these are basically equivalent methods. Okay, so let's see this. You can see this method number 2, remember, this is applicable only for postfix SDT, and yes, here we have postfix SDT because all the semantic rules are placed at the right end of the production bodies. So in this method number 2, what we do here, basically the semantic actions are executed immediately after the reduction. Along with the reduction, the semantic actions are executed. Now in this method 2 also there are two ways. The way one, that is from the rightmost derivation point of view using rightmost derivation, and the way 2, that is using parse tree. Okay, let's see both of them. First, let's see using a rightmost derivation. So what I will do, for this input string, I will create a rightmost derivation. Okay, let me create rightmost derivation. For this input string, I am creating the rightmost derivation. Your rightmost derivation will start from the start variable. Yes or no? Let me call this production 1. Let me call this production 2. Let me call this production 3. Okay, so your rightmost derivation will start from the start variable. Then this start variable, I will apply the production 1. Okay, and I will go to xxw. xxw. Next, you can see that we only have one non-terminal here, that is w. So I need to replace it. There is only one w production, so I need to use it. So the third production I will use, and I will get xx sz. Again, here you only have one non-terminal, so I have to expand it. So here you can see that I need 4xy double z. So here this s, I will use the first production, and it will go to xx wz. Okay, very simple. Now again, here there is only one non-terminal. Okay, so that I need to expand, and there is only one w production. So basically I need to apply this third production, and we will go where, when we apply this third production, then we will go to x. Okay, so let me write here. From here, the third production I will apply, and we will go to x x x x s z z. Okay, next you can see that this s will go to y. Okay, so x x x x y z z means the second production we are applying. Okay, so that's it. So this is the rightmost derivation that we got. Now remember one thing, I told you that the bottom parser will do what this rightmost derivation is doing, but in the reverse order. Okay, so the rightmost derivation is in this order. The bottom parser will start from here. Okay, yes or no? So you can see the bottom parser will start from here. The bottom parser. The bottom parser will start from here onwards. In the reverse direction it will go. Whatever this rightmost derivation is doing, just do it in the reverse order. That is your bottom parsing. Okay, so you can see what the bottom parser will do. You can notice this rightmost derivation, it is applying this second production here. So the bottom parser, what it will do, it will apply the second production in the reverse order. Yes or no? Notice one thing, the rightmost derivation is basically doing this, that this s you are replacing with y. The second production, this rightmost derivation is applying. What the bottom parser will do, it will apply the same production in the reverse order, means this y we will replace with s. And when you apply a production in the reverse order, that is called reduction. That is called reduction. And I told you that in this method too, the evaluation of postfix SDT, along with reduction, you execute the corresponding semantic action, like this, which production you are reducing, the second production you are reducing, right? So the production that you are reducing, so the corresponding semantic action you can execute here. So remember, here we are reducing, what we are reducing, reduction of production 2, of production 2. Is this clear? So along with the reduction, what we need to do, along with the reduction, because of this reduction, along with the reduction, we need to perform this, we need to execute the semantic action corresponding to this production that we are reducing. So I will print 2. Okay, yes or no? Is this clear? So you can see what the bottom parser will do, it will print 2. Very simple. So remember, 2 has been printed. Okay, we will print 2. So here let me write the output. In the output, remember, 2 has been printed. Okay, very simple, right? I hope this also you are finding very interesting. that how we are solving this question with another method, that is using rightmost derivation. Okay, and all the concepts are very intuitive. Okay, I'm just using the concept, nothing else. Next, let's see the next. You can see what is the next step. In the next step, the bottom up parser will apply this production 3 in the reverse order. You can see that this rightmost derivation is basically applying this third production. This W is going to SZ. Now what the bottom up parser will do? The bottom up parser will basically do that this SZ will go, this SZ will go to W. Okay, yes or no? The bottom parser, what it will do? It will reduce this SZ to W. Means this third production we are reducing. This is also a reduction. Okay, yes or no? You can see that this is also a reduction. This is the next reduction, I can say. When you apply a production in the reverse order, that is called reduction. So here, this is the next reduction. And I told you that along with the reduction, immediately after the reduction, you execute the semantic action. So here we are reducing the production 3. So the corresponding semantic action with the production 3, that we will execute. So here we will print 3. Okay, we will print 3. Yes or no? Now let's quickly see. Next, what is the next reduction? You can see next, this first production we will reduce, then this third production we will reduce, then this first production we will reduce. Okay, so basically you don't even have to do this. You just check that, okay, now the next will be this, next this we will reduce, then next this we will reduce, then next this we will reduce, then next this we will reduce. So you can see after 2 3 the first production we will reduce, and when you reduce the first production, then the semantic action you will execute. So means you will print 1. Then this third production you will reduce. So this semantic action associated, or I can say the semantic action corresponding to the production 3, that we will execute. So we will print 3. Next, at the end, you can see we will reduce the first production, and you are reducing the first production. So the semantic action, the corresponding semantic action we will execute. So we will print 1. This will be your output. 2 3 1 3 1. You can see with the previous method also 2 3 1 3 1, the same answer we got. I hope you understood. Okay, I hope you loved this method also. That all you have to do, remember, you just create the rightmost derivation, and then you don't even have to do anything else. Just create the rightmost derivation and just look at these productions that are applied by the rightmost derivation in the reverse order. The productions applied by the rightmost derivation, you just see them in the reverse order, because the rightmost derivation is applying the productions in this order, but the bottom parser will reduce these productions in this order. Okay, so I can say the order of reduction is basically the reverse of the order in which these productions are applied. These productions are applied in these productions are applied in this order by the rightmost derivation. The bottom parser will reduce them in this order. Okay, means in the reverse order. So I hope you found this method also very useful. Now let's solve the same question with another method, that is using a parse tree. Same method 2, but way 2. What is method 2? Remember, the method 2 is saying that if you have a postfix SDT, here you have a postfix SDT. So the method 2 is saying that only for postfix SDT, how we can evaluate, very simple. The semantic actions we can execute immediately after a reduction. Okay, now what I'm going to do? Now I'm going to solve the same question with our third method, means the method 2 way 2, using a parse tree. What I will do? The step number 1, let me tell you, that is you create a parse tree without semantic actions. Okay, so let me tell you the step 1, build parse tree. Build parse tree without semantic actions. Okay, without semantic actions you build parse tree. Then what the step number 2? Step number 2, that is you perform left to right depth first. Okay, then what are the step number 3? Step number 3 is that execute semantic actions immediately after a reduction. Okay, execute semantic actions along with reduction. Okay, along with reduction. Very simple. Okay, so let's apply this method and to solve this, and let's solve this question. So let's make the parse tree without semantic actions. So what I will do, very simple. I will the root node, that is the start variable. Now this s is going to x w. Next this w is going to s z. Then this s is going to x w. Then this w is going to s z, and then this s is going to y. Okay, yes, so this is the parse tree that we generated. You can see double x y double z. Yes, okay, so this is the parse tree that we have generated. So first you build the parse tree without semantic actions. This is a parse tree without semantic actions. Now what you do, now you perform left to right depth first. Okay, let's perform. So this is the step 1, remember, this is the step 1. Now let's see the step 2. In the step 2, what we will do, we will perform left to right depth first. Okay, so let's perform left to right depth first. You can see I'm going like this, I'm going like this. Here this is not a reduction, right? Reduction means when you apply a production in the reverse order. So here there is no production called s going to x. This is the production, s going to xxw. So when this xxw you replace with s, this is called reduction. Reduction means when you apply a production in the reverse order, like this xxw, this when you replace with s, then that is called reduction. Like this y when you replace with s, this is called reduction. This sz when you replace with w, this is called reduction. Okay, so you just keep going left to right depth first. Okay, here this is not a reduction, again not a reduction. Okay, just keep going. Okay, not a reduction, keep going. Okay, keep going. Yes. Here you notice that this is your reduction number 1. Okay, because here you can see this y you are reducing to s, this y you are reducing to s. Is this clear? So here basically we are reducing the production to let's call it production 1, let's call it production 2, let's call it production 3. So here basically you are reducing production 2, and because you are reducing production 2, so execute semantic actions along with the reduction. Which production you are reducing? Production 2 you are reducing. So the corresponding semantic action with this reduced production, the production that you are reducing, so the corresponding semantic action you execute. So we need to print 2. So we will print 2. Okay, so here let me write the output. The output will be, we will print 2. Okay, very simple. Now just keep going. Okay, now you can see sz going to w. This is the next reduction. Now you notice sz going to w. This is the next reduction. Okay, is this clear? This is the next reduction. So here which production we are reducing? The production 3. Okay, sz we are reducing to w. Sz we are reducing to w. So production 3 we are reducing. So the corresponding semantic action we will execute. Okay, you can see execute semantic action along with reduction. So you are reducing the production 3, the corresponding semantic action you execute. So we will print 3. Okay, keep going. Next you can see that there is next reduction, that is xxw to s. xxw you are reducing to s. Yes or no? xxw we are reducing to s. So means this first production we are reducing, so the corresponding semantic action we will execute. So we will print 1. Okay, keep going. Yes, the next reduction we got here, we are reducing sz to w. We are reducing sz to w. Okay, means this third production we are reducing. So the corresponding semantic action we will execute. So we will print 3. Okay. Then after that, you can see, then this, then you can see this xxw we are reducing to s. Xxw we are reducing to s. The first production we are reducing. So the corresponding semantic action we will execute. So we will print 1. Okay, so the answer finally will be 23131. The same answer we got with the previous methods, 23131. Okay, so I hope you understood. So for this same question, we have seen multiple methods. I hope you loved each and every method. I hope you understood each and every method. Okay. Let's solve GATE 1996 question. Consider the syntax directed translation scheme SDTS. So here this syntax directed translation scheme is given to us. Notice one thing, that this translation scheme, this is Postfix SDT. Notice this is Postfix SDT. What is Postfix SDT? Postfix SDT, this is a translation scheme in which the semantic actions are placed at the right end of the production bodies. Here you can see all the semantic actions are placed at the right end of the production bodies. So this is a Postfix SDT. And I told you one thing in this lecture, that Postfix SDT evaluation, how to evaluate Postfix SDT. So this Postfix SDT, we can evaluate in bottom-up parsing fashion. With help of bottom-up parser, we can evaluate this Postfix SDT. What we will do? Very simple. Along with the reduction, we will execute the semantic action. Okay, yes or no? Okay, so in the previous question also we have done this, and in this GATE exam question also we have this Postfix SDT. Now, what this question is saying? The question is saying that an LR parser, which is a bottom-up parser. So LR parser executes the actions associated with the productions immediately after a reduction by the corresponding production. Actually, what this line is given to you, this is basically a evaluation method for Postfix SDT. Yes or no? This is only for Postfix SDT, correct? This is only for Postfix SDTs. Okay, I told you that to evaluate Postfix SDT, one method is the general method, which is working for all the SDT. Okay, that method also we will see in this question. Basically, this question we will solve with multiple methods. We will see general method, which will work for all the SDT, whether you have Postfix SDT or whether you have some SDT which is not Postfix. Okay, but remember, for Postfix SDT, we have a special method. That is what we can do. Basically, we can execute the semantic actions immediately after a reduction. Okay, so let's see. Draw the parse tree and write the translation for the following sentence. This is the sentence, and for this sentence we need to write the translation. Means what will be the output for this input. Okay, for this what will be the translation. So let's solve this question with multiple methods. First, method 1, that is the general method for all the SDTs. I told you there is a evaluation of syntax directed translation scheme. This is the general method which is working for all the SDTs. And in this method, what we do? Very simple. We first build a parse tree, including the semantic actions. Including the semantic actions, you build a parse tree. Then you perform left to right depth first order. And during this left to right depth first order, as soon as you reach a semantic action, immediately execute it. So let's solve this question with this method. You can see this is our SDT, syntax directed translation scheme, and this is the input which we need to translate. Okay, so let's first create the parse tree including the semantic actions. Okay, so the root node, the root of the parse tree, that will be the start variable. So this is the start variable E. Now here what I want A plus B star C plus D. Okay, so what I will do, I will go to E going to, it's like this. Remember, I am creating the parse tree, I am constructing the parse tree including the semantic actions. So here basically E will go to E star E print dot. Okay, so remember this E will go to E star E and print dot. Print dot. Okay, the semantic action, let me use a different color so that it is clearly visible that this is a semantic action. So print dot. Okay, very simple. Next, you can see, so we got this star. Now from this E, I want bracket A plus B. Okay, so you can notice this E will go to, this E will go to this parenthesis E close parenthesis. Similarly, this E will go to parenthesis E right parenthesis. Okay, now you can see this E, using this we need to generate A plus B. So you can see this E will go to, notice this E will go to E plus E print plus. Okay, because we are constructing the parse tree including the semantic actions. Okay, so you can see E will go to E plus E and this semantic action print plus. Okay, very simple. Now next what? Next you can see that this E will go to basically ID. Okay, so you can see that this E, notice this E will go to ID, print ID name. Okay, so remember this E will go to ID. Here, this is the semantic action, print ID name. Okay, because this ID, this is basically a token. So we need to print the lexical value, or I can say ID dot name. Okay, similarly for this E also, this E will go to ID and here print ID name. Okay, the same thing will happen for this E. Now notice what we got so far. We got A plus B star. Now this E, where this E will go? Notice this E will also go to E plus E. Okay, so this will go to E, then plus, then E, and then print plus. Okay, print plus. Then finally, you can see that this E will go to ID, and on another side, you print this ID name. Okay, and similarly, this E will go to ID, and here print ID name. Okay, that's it. So we have created the parse tree including the semantic actions. Now what we need to do, basically this was your step number 1, that this is the parse tree including the semantic actions. Parse tree including semantic actions. Okay, now what we will do? Now we will perform left to right depth first. Okay, as soon as we will arrive at any semantic action, we will immediately execute it. Okay, so you can see, let's go left to right depth first. Okay, so you can see that you are going like this basically. Okay, then you are going like this, then like this, and yes, print ID. We need to print ID. Okay, let me tell you one more thing here. In this actually, in this parse tree, here notice this ID is basically A. Okay, this ID is basically A, this ID is basically B. Sorry, this ID is basically A. This is a semantic action. This is not ID, this is basically semantic action. This ID is basically B, this ID is basically C, this ID is basically D. Okay, is this clear? So it's like this. This is A, then this is B, then this is C, then this is D. Okay, now let's see. So here, very simple. You perform the left to right depth first. Okay, just keep going like this. Now here, this is the semantic action. As soon as you reach at a semantic action, immediately execute it. So output will be what? You can see print ID. We need to print ID. Which ID I will print? You can see here print ID, which ID I will print. You can see this semantic action is associated with this production. Okay, you can see with this production. Okay, so you can see this semantic action is associated with this production. So here, this ID A I will print. Okay, yes or no? This ID A we are going to print. So this A we have printed. Then just keep going. Okay, just keep going until you arrive at a semantic action. Here we need to print ID. Which ID I will print? This semantic action is associated with this production. So here this ID B I will print. Okay, keep going until you arrive. So you can see that keep going like this until you arrive at a semantic action. So here semantic action, that is print plus. Okay, let's print plus. Then you keep going keep going left to right until you arrive at a semantic action. Semantic action, print ID. Which ID I will print? Print ID. So this semantic action is associated with this production. So here this C I will print. Okay, just keep going print ID. So this D I will print. Keep going print plus. So this plus I will print. Then you can see keep going like this. Then print dot. Okay, at the end dot I will print. That's it. So your output will be what? That will be AB plus CD plus dot. This is the output. I hope you understood. Okay, so this is method 1 to solve this question. Now let's solve this question with method 2, because in this question the SDT that is given to you, that is postfix SDT. This method 2, this is only for postfix SDT. So how to evaluate postfix SDT? Very simple. What we will do, the semantic actions we will execute along with the reductions. Okay, so let's solve this question, this same question let's solve using this method number 2, which is only for postfix SDT. Now in this method 2 also I will solve using rightmost derivation. Also I will solve using parse tree. Okay, just for sake of practice, just for sake of learning, I am solving the same question with different methods, but I will give you a conclusion like which method you can apply by default, or I can say which is the best method to apply in almost all the questions, or I can say in all the questions. Okay, that is actually this method. Okay, if you have postfix SDT, then what you do, then this method actually, like using parse tree, semantic actions we will execute immediately after reduction. So this method is actually overall the best method. Okay, but let's, just for understanding purpose, let's solve this question using rightmost derivation also. So first what I will create, I will generate a rightmost derivation. Okay, so let's generate rightmost derivation. Okay, so to generate the rightmost derivation, you can see I will start from the start variable. So we are starting from the start variable. Now let me number the productions first. Let me call this production 1, let me call this production 2, production 3, production 4. These are the numbering of the productions. Okay, now so I will start from the start variable. Now you can see that I will go to where I will apply the production 2. Okay, we will apply production 2 and we will go here E star E. Now you can see that we are up, remember we are making rightmost derivation. Here we have two non-terminals. So the rightmost non-terminal we need to expand. Okay, this rightmost non-terminal we need to expand. So from this E, I want bracket E. So this fourth production I will apply and I will go to E star this. Again, you have multiple non-terminals here. So in the rightmost derivation, we will expand the rightmost non-terminal. So this, the rightmost non-terminal we will expand. So you can see this E star, and inside this E will go to E plus E. Okay, which production we are applying? You can see the first production we are applying. Okay, next you can see again we have multiple non-terminals. So the rightmost non-terminal we will expand. So this E will go to id. Okay, so you can see this e will go to id, e plus this e will go to id, and this id will be basically d. Okay, you can see this is d. So this will be like this. Here which production you are applying? The third production you are applying. Here again you have multiple non-terminals, so the rightmost non-terminal we will expand in the rightmost derivation. So this e, again the third production we will apply, and we will get e star c plus d. Okay, so this e will go to id, which is c. Okay, next you can see that now there is only one non-terminal here, so this non-terminal we need to expand. So I will apply the fourth production, and we will get star c plus d. Okay, then here again I have only one non-terminal, so I need to expand it. I will apply the first production, and what I will get e plus e star c plus d. Then again you can see we only have, actually you have multiple non-terminals, so the rightmost non-terminal we will expand. Okay, so you can see that this rightmost non-terminal we will expand in the rightmost derivation. So we will apply this third production. In the third production, what will happen? We will get e plus this e will become, this e will go to id, which is b. Okay, which is b. So star c plus d, and then you can see that there is only one non-terminal, so that we need to expand. So this e will go, I will apply the third production, and this e will go to id, which is basically a. So I will get a plus b star c plus d. Okay, that's it. We got our rightmost derivation. Now let me tell you, your work is over, because I told you that what this rightmost derivation is doing, the bottom parser will do it in the reverse order. And you can see that the reverse of a step in this derivation, that is called reduction. Okay, you can see this is single step, this is single step, this is single step. Now in the reverse direction, the reverse of a single step, that is called reduction. Okay, yes or no? So remember, the rightmost derivation is applying these productions in this order, like first production 2, then production 4, production 1, 3, 3, 4, 1, 3, 3, like that. Okay, so the rightmost derivation is applying these productions in this order. The bottom up parser will reduce these productions in the reverse order, because what this rightmost derivation is doing, the bottom up parser will do everything in the reverse order. Yes or no? So you can see that these productions that the rightmost derivation is applying, the order of productions is this. So the bottom up parser will reduce these productions in the reverse order. Okay, so here basically what the bottom up parser will do, it will reduce the production 3 first, then production 3, then production 1, then production 4, then production 3, then production 3, then production 1, then production 4, then production 2. And I told you that semantic actions will be executed immediately after the reduction. Okay, yes or no? So here what will be the output? You can see what the bottom up parser will do. First it will reduce production 3. Along with reduction, you execute the semantic actions. So remember, first the bottom up parser is reducing production 3, and production 3 has this semantic action print id name. Okay, so here which id name will be printed? The production 3 has this semantic action print id name, but actually which id name will be printed? So you just notice that here we are reducing this production 3, and basically this e was going to a, so this a will reduce to e. Yes or no? Okay, do you agree with me? Very simple point I am saying. See, I am saying that look at what this rightmost derivation is doing. This is going to this. Okay, this is going to this. What the bottom up parser will do? The bottom up parser will do this, that okay, this a will go to e, means this a will reduce to e. So very simple point that we are reducing the third production, so the corresponding semantic action we need to execute, we need to print id name. Which id name we will print? So that is basically your a. Okay, yes or no? So this a I will print. Next again you can see that this third production we are reducing, So again, the corresponding semantic action we need to execute. So again, we need to print the ID name, but which ID name we will print? So for that, you notice that here you can see that this E was going to be, yes or no? So the bottom parser, what it will do? It will reduce this B to this E. Okay, yes or no? So this is the point here that we will print the ID name. So this B I will print. Next, you can see we are reducing production 1. When you are reducing production 1, then the corresponding semantic action will be executed. So this plus will be printed. Okay, then you can see we are reducing production 4. In the production 4, there is no semantic action, so there is nothing to do. Okay, we are reducing production 4, but in the production 4, there is no semantic action corresponding to this production 4. So there is no semantic action to execute. Okay, then you can see that next again you can see that we are reducing production 3. So we are reducing production 3, so this semantic action we need to execute. So we need to print ID name. So which ID name I will print? You can notice here basically this C will reduce to E. Yes or no? This C will reduce to E. So here this C I will print. Next, you can see again this third production we are reducing. So we need to execute the corresponding semantic action. That means we need to print the ID name. And which ID name I will print? Very simple. You can notice actually here this E was going to D. So this D will reduce to E. So this D I will print. Then you can see we are reducing production 1. So the corresponding semantic action we will execute. So we will print plus. Then we are reducing production 4. The production 4 has no semantic action corresponding to it. So there is nothing to do. Next, you can see at the end, we are reducing production 2. When you reduce production 2, then the corresponding semantic action we need to execute. And that is print dot. So we will print dot. Okay, that's it. This is your answer. I hope you understood. Okay. So very simple, right? Just for understanding purpose, this method also we have seen using rightmost derivation. Now the same question, let's solve using this method 2, but using parse tree. What is method 2? Method 2 is only for postfix SDT. This is postfix SDT. So this method 2 is basically saying that semantic action will be executed immediately after the reduction, or I can say along with the reduction, the semantic action will be executed. Now in this method 2, the way to that is using parse tree. So let's see this. I told you the steps in the previous question. We have already seen the steps. What are the steps? So let me write it. The step number 1, that is build parse tree. The step number 1, that is build parse tree without semantic actions. Without semantic actions. Okay, this is the step number 1. Of course, what are the step 2? Step 2 is left to right, depth first traversal. Depth first traversal. Okay. And what are the step 3? Semantic action along with reduction. Semantic action along with reduction. Okay, and what is the reduction? When you apply a production in the reverse order, that is called reduction. Okay, so let's see this. First, we are going to generate the parse tree. So first, let's build the parse tree without semantic action. So the root node, that is the start variable E. Okay, what I want A plus B bracket star C plus D bracket. So you can see this E will go to E star E. Okay, then you can see this E will go to bracket E bracket. This E will also go to bracket E bracket. Then you can see that this E will go to E plus E. This will go to E plus E. This will also go to E plus E. Then you can see that this E will go to ID, this E will go to ID, this E will go to ID, this E will go to ID. Okay. Now, of course, you can see that this ID is a token. So what is the lexical value? So you can see that this ID is basically this ID dot name, that is basically A. This ID dot name is B, this is C, this is D. Okay. So that's it. We got our parse tree. This is the step number 1 completed. This is the step number 1 completed. Okay. Now, what is the step number 2? That is, we will perform left to right depth first. Okay. So you can see that we are performing left to right depth first. And when you reduce, along with reduction, we will execute the semantic action. And what is a reduction? I told you reduction means when you apply a production in the reverse order. So remember, when this E plus E we replace with E, then that is called reduction. When this E star E we replace with E, this is called reduction. When this bracket E bracket we replace with E, this is called reduction. When this ID we replace with E, this is called reduction. Okay. So just keep going left to right, depth first. You can see this is not a reduction. Okay. You can see this bracket going to E. This is not a reduction, because reduction simply means when you apply a production in the reverse order. Okay. Means when this bracket E bracket, when you replace this with E, this is called reduction. Okay. So basically just keep going, keep going, keep going. Now notice here we got our first reduction. Okay. Notice here we got our first reduction. You can see ID we are reducing to E. Okay. ID we are reducing to E. ID we are reducing to E. So here what we will do, along with reduction, we need to execute the semantic action. So here ID is A. Okay, you can see we are reducing ID to E. So here this is the semantic action. We need to print ID dot name. Okay, we need to print ID dot name. So here ID dot name, that is A. So that we need to print. Okay, so we need to print A. Now let's see the next. Keep going. Keep going, keep going. So you can see keep going. Next, you can see that we got our next reduction. Again, ID is reducing to E. Again, you can see this ID is reducing to E. This is reducing to E. Okay, so here, along with reduction, we will execute the semantic action. So we need to print ID dot name. Okay, what is the ID? ID is B. So this ID dot name, we need to print B. Very simple. Keep going, keep going. Now notice, we got the next reduction now. We got our next reduction now. What is that? The next reduction is basically this. E plus E, we are replacing with E. Yes or no? E plus E, we are replacing with E. So this is the next reduction we got. And along with reduction, you will execute the semantic action. So here we will print plus. Okay. Keep going, keep going. So keep going like this. And here again, we got our next reduction. This next reduction we got here. Okay, notice this bracket E bracket, we are replacing this bracket E bracket, we are replacing with E. This bracket E bracket, we are replacing with E. So this is a reduction. Along with the reduction, we will execute the corresponding semantic action. There is no semantic action corresponding to this production. Okay, so there is nothing to do. So just keep going, keep going. Okay, keep going, keep going. Keep going like this, like this, like this, like this. And here we got our next reduction. You can see this ID we are reducing to E. This ID we are reducing to E. So the corresponding semantic action we will execute. So we will print the ID name. Here the ID name is basically C. So this we will print. Okay. Next, you can see just keep going, keep going, keep going, keep going. Then here you can see we got our next reduction. That is ID is reducing to E. This ID is reducing to E. So again, this semantic action we will execute. We will print the ID name. The ID name is basically D. So that we will print. Okay. Then Then we got our next reduction. What is our next reduction? You can notice this is our next reduction. E plus E we are replacing with E. Okay, E plus E we are replacing with E. So the corresponding semantic action we need to execute. So we need to print plus. Okay, then you can see, just keep going. Okay, like this, like this. We got our next reduction here. We got our next reduction here. Notice this is the next reduction, that bracket E bracket we are replacing with E. Bracket E bracket we are replacing with E. So this reduction, but there is no corresponding semantic action to execute. Okay, so just keep going. Now you can see that our last reduction we got here. Our last reduction, that is, you can see E star E is replaced by E. E star E is replaced by E. So you can see this is the last reduction, and the corresponding semantic action will be executed. So we will print dot. Okay, this dot we will print. So finally the output will be this one. Okay, I hope you understood. That's it. Okay. So that's enough for this lecture. In the next lecture, we will solve the remaining GATE PYQs based on SDT. Also, we will study SDD and all GATE PYQs. Okay. So thank you everyone. Please share your feedback with me. Did you like this session? Did you understand each and everything? If you have any doubt, you can ask in the comments. Let us know your feedback. Let me know your feedback. Okay. Thank you.